Good morning, everybody. Let's get started with our pre-sessions. So we'll go first a review of the breakout sessions from yesterday. So if I could invite the leads up from each of the breakout sessions to give a short overview of the topics discussed.
Good morning, everyone. We're from this Earth system modeling sessions in the North Auditorium. And then we have very fruitful topics yesterday, and then discussed about a lot of the things happening in the theme. It discussed about hybrid quantum classical workflows and defining quantum advantages in climate modeling, and then remap to pilot studies and collaborations. So first things we summarize here is encoding climate problems onto the quantum hardware remains a core technical barriers right now. So there's no clear method exists for the encoding nonlinear differential equations like PDEs and multi-physical systems as quantum system. And also even simple nonlinear system lack efficient solvers. And we also point out that existing solvers are problem specific and not generalizable. And hardware noise and limited qubit count constrain current NISQ era applications. Field has shifted to error mitigations rather than error corrections. So the pathway forward would be develop the algorithms for nonlinear systems with demonstrated scaling behaviors, prioritize scale-focused problems suited to quantum approaches rather than forcing classical framing onto quantum hardwares. And second point we point out is discuss about it quantum advantage. Quantum may be slower than GPU-based classical computing for some problematic problems. Some quantum mechanical problems are solvable classically. And then quality matrix require reference point for judging the solution's quality. And the second bullet point here is the uncertainty qualifications for the quantum solutions is nascent. Some work exists, but is focused on optimizations. And path forward here, we discuss about establish benchmarking analogous to operational center matrix, like such as energy, time, data per task, and apply these to quantum workflow, potentially via quantum machine learning. And the third point we discuss is data transfer and representations are main bottlenecks. About 80% of the computing power is consumed transferring data between classical and quantum system right now, and no established quantum native grade or representation for Earth observation data, and Ising model mappings demonstrates one viable rethinkings. And quantum machine learning has shown promise in identifying parameters more robustly than classical parameterizations, but training data biases may propagate to outputs. So it's important to remember all the progress we have made in quantum application in recent decade. So there's a long way to go. And the path forward would be developing quantum ready data representations and data compressions techniques. And fourth point here is community building and access are prerequisites for the pilot studies. Most quantum computing capacities reside in private industry. Federal funding mechanisms should foster public-private partnership, like NVIDIA's CUDA or crowdsourcing models. And barriers to entry is high for climate scientists without quantum background. Existing resources, including Penny Lane documentations and IBM's VQE tutorials is very helpful for beginners. And benchmarking between domains and quantum expert is already occurring. NASA JPL, for example, enable two-way education is very important moving forward. So path forward would be recommend working groups, hackathons, and summer schools, encourage interdisciplinary fundings, calls, provide shared access to quantum hardware or simulations, emulator hardware plus expert stuff, prioritize open source tools and toy problems as learning vehicles. So overarching takeaways here from our breakout sessions is how do you translate a climate model problem into a form a quantum computer can actually solve? No established method exists yet for encoding nonlinear PDAs, defining quantum native data representations, or standardizing matrix for quantum advantage in climate modeling. And second bullet is access and expertise barriers are equal obstacles to hardware limitations. And third point here is pilot studies require scaffolding before hardware deployment. prioritize toy problems, simulated hardware, interdisciplinary working groups, summer schools, and funding support to build community expertise and establish meaningful benchmark for quantum advantage is very important. So here I think everyone came to our breakout sessions, and also Maribas created this slides for us. And thank you for everyone contributed this brainstorming work. Thanks.
Hi, good morning, everyone. I would first of all like to thank Rubaiyat and Ruben for helping with the note-taking and moderating the session. Now, for our breakout session, we had the same identical 3 sets of broad pointers we discussed. So first of all, we identified that all of model initialization, the high dimensionality of the Earth system modeling problem, and temporal coherence, which is to say that advancing the current state requires knowledge of the past states. Sometimes all of these factors form key bottlenecks to simulating high fidelity Earth system models using current quantum algorithms. However, even when these problems are solved, we believe the problem of nonlinearity inherent in the chaotic system would continue to be a blocker for future quantum algorithms. And someone pointed out yesterday that NISQ era quantum algorithms continue to exhibit poor performance even on simpler linear problems like 1D diffusion. And so in the meantime, while we improve on that aspect, we can either use these algorithms to solve linearized components of Earth system models alone, and we can define what the linearized components would be, or we first continue to perfect these algorithms to perfectly simulate the linear and quasi-linear systems before moving on to more complex high Reynolds number turbulent regimes. Now, subgrid parameterizations and non-convex parameter optimizations were identified as 2 key candidates, 2 viable candidates for hybrid implementation. And when I say subgrid parameterizations, atmospheric chemistry and radiative transfer would be 2 great candidates. There's ample potential for improved accuracy and speed up because a lot of these parameterizations have biases, require more validation, things like that. And non-convex parameterization optimization, parameter optimization is a low-dimensional problem for individual parameterizations, but it can also be formulated as a joint calibration problem and get massive improvements in performance. Now, depending on the problem, to address high dimensionality, what we can do is use spectral transforms to reduce the dimensionality of the problem and bring it to a lower dimension, and further use techniques like shadow tomography and quantum neural networks. Some of it we saw yesterday. These can be used to emulate these lower dimensional systems instead. Now, when it comes to defining quantum advantage for climate modeling, of course, we can use straightforward metrics like computational speed up, improved accuracy of the simulations, reduced power consumption by the algorithms and hardware, and data compression. And these could be used to broadly define quantum advantage. However, for the problem of joint parameterization calibration, a combination of computational speedups and more physics-informed metrics like process variability and the generalizability of these processes to multiple forcing scenarios, they can serve as decisive metrics. And these are inspired from the classical way of Earth system modeling. Now, these metrics should continuously be first tested on processes that are already known to have quantum advantage, and then they should be used to create baselines for future processes. And these could be as has been done for algorithms like Shor's algorithm, Grover's algorithm, and so on. And there was a nice word of caution from Holland yesterday, who said that we should wisely not continue to chase quantum advantage, quote unquote, but rather just persistently move in the direction where we continue to innovate new algorithms, develop new gates for implementation in quantum computers until we reach a point where we naturally have a quantum advantage. And he gave a nice iPhone analogy, which I liked. It was more related to how when iPhones were launched, we went from using wired telecommunication to wireless telecommunication. Basically, at that time, it was a big thing, but now, even 20 years later, just 20 years later, we don't think much about it. We are focusing on more other aspects of what the phones could do, right? And they could do so much more than what they could do 20 years back. So yeah, that could be a nice goal going forward. Now, the group identified a couple of pilot studies that could be the focus for the next 2 to 3 years. And there was a unanimous agreement that simulating nonlinear fluid dynamical systems in their entirety might take more than 3 years. It's not a 2 to 3 year problem. But then the parametric estimation problem would be an excellent candidate for such 2 to 3 year pilot studies. And there's a straightforward way to validate our results as well and quantify improvements in the parametric estimation using straight up observational validation. And then we could move to a higher dimensional problem like developing new subgrid scale parameterizations for atmospheric chemistry, radiative transfers, and to better data assimilation algorithms. And in the meantime, there should be a constant push to create new and simpler test beds for testing linear systems and new benchmarks to evaluate quantum algorithms. And parallelly, as research has been going so far, we should continue research on simulating linear and quasi-linear systems. And these systems could be simple energy balance models, QG dynamics on quantum computers. And our aim should be to continue to increase the fault tolerance. And then finally, we agreed that communication between the climate modeling community and the quantum research community is really important, really critical. What the climate modelers can do is closely collaborate with quantum researchers, quantum physicists, quantum engineers, and formulate the problem in a way that is palatable or more understandable to the quantum research community. And that could bridge the gap between the two fields and provide pathways for new innovation. And finally, we discussed what could be the mechanisms to reduce barriers to entry. And here again, we thought communication could further help. When I say communication here, I mean more like climate scientists can continue to work together with quantum researchers, but learn how to use quantum technologies and how to use the most appropriate quantum algorithms for their problem. And this could be in form of scheduling regular calls with researchers both in academia and industry. And this could also, again, help industry researchers and academic quantum researchers develop a much deeper understanding of the climate problem and formulate these problems better. Finally, it would help if we could delineate all the existing problems that need to be solved into buckets, like easy bucket, easy problem, medium problem, hard problems. And then that would also enable more engagement with by industry researchers. Finally, open platforms always help. Having all the platforms and libraries, making them open source. Some libraries like Qiskit and PNNL exist. Qiskit platform also provides 10 minutes of free quantum computing time to free users. And then in addition, having easily accessible Jupyter notebooks and workflows that climate modelers can easily adopt, they could really help speeding progress on the quantum modeling front, climate modeling front. Finally, this one is important. This need for a dedicated and accessible quantum computing cluster for climate modeling that climate modelers can use, and not having to worry much about the costs. That could also help reduce the barriers to entry. Those are the conclusions of the second session. Thank you.
Thank you, Aman. I'd like to invite our last lead up to give an overview. I believe this was the quantum sensing breakout session.
Okay, for quantum sensing, talked about the measurement challenges, and we wanted to identify some climate measurements that not able to make currently at the level of precision, resolution, coverage that we need with current sensors, and would prioritize these a little bit. So the ocean heat content, salinity, and movement was one of them, especially looking at different levels below the ocean surface, looking at how these can bound the uncertainty in some mixed layer depth. Okay, sea level rise due to thermal expansion of the ocean surface. Second one was water availability, which would include both things like soil moisture, water stored in the soil, as well as subsurface aquifers. That's important because of predictions on hydroelectric power, planning for droughts, things like agriculture and fields like that. Yeah, so one of the other problems we identified is when combining different sensors like active and passive microwaves, they have different resolutions, different footprints, different coverages. So could a quantum sensor such as we talked about the Rydberg receivers, whether we could do both active and passive with the same sensor, the same footprint, whether that would be an advantage with quantum sensors. Measuring greenhouse gas concentrations, one of the problem brought up is there's this large number of species of greenhouse gas, and we only can monitor a few of those. But by having very fine multispectral measurements of all the different absorption bands, we might have a better way of cataloging the large variety of greenhouse gas emissions and concentrations. Identifying the atmospheric boundary layer. is a very important problem, and it's difficult to do in clean air without relying on the motion of precipitation and clouds. And lastly, yeah, the thermodynamic profiling of the atmosphere, temperature, and water vapor, and winds. I don't know if there's really any priority here. These are the ones we brought up in discussion. Okay, so we talked about some quantum sensing solutions to these challenges. One of them is just improved position navigation and timing, especially in areas where GPS doesn't work very well. So, for example, underwater. So I know there's a lot of work in PNT using quantum techniques for cases in which GPS or GNSS is unavailable for other reasons, but underwater was one possibility that we being able to better map in situ measurements underwater could be one application. The multimodal broadband sensing, which was mentioned earlier, but now we're talking about the sensing aspect of it, using this Rydberg sensor, which is tunable over a wide range of frequency, basically the entire microwave spectrum. JPL's talked about using that for signals of opportunity, which may be, again, a combination of the active and passive microwave with the same resolutions. And we mentioned greenhouse gas concentrations earlier, details of the types of instrumentation, the Fourier transform spectrometer with the frequency combs, or the very fine resolution of the different emission bands or absorption bands to identify all of these concentrations that we're not currently tracking. Implementation, integration with the quantum computing. I think those also talked about earlier in terms of making the measurement in a form that works well with quantum computing and without a lot of this translation between setting the problem up. In terms of the infrastructure, test beds, we did have a lot of discussion about that. I just hit a couple of the key points. Of course, all the aspects of building a sensor that will work in space, and it also was brought up, there's more to climate sensing than just space sensors. But here we're just talking about spacecraft instrumentation. So the engineering involved in radiation proofing, vibration resistance, lasers that are space qualified. All of these things are expensive parts of the path to an operational system. There are also some discussions about OSSIs, observation system simulation experiments, where we can actually look at what requirements on a specific measurement do improve a climate forecast. So we can look at simulations of climate systems and then look at different measurements at different resolutions, different coverages in that to see what the improvement would be. Yeah, so the idea is setting up an institute, also maybe some courses, short courses on these different techniques. One of the things myself and some of the other faculty members were very interested in is what type of curriculum would be needed to bring an understanding of quantum systems into, in my case, a space engineering program, or into, say, a geophysics program. What will the course structure look like, and how can we put that together to better prepare researchers to use these techniques in the future? Okay, non-technical challenges. Cost, the accessibility of emulators and simulators. That was also another thing we brought up. That's in the technology development of these new sensors. There needs to also be in parallel some development of a model for the sensor, or an emulator, or an air model that could be used for these studies if the performance it doesn't follow the same type of performance metrics that, say, a radar or a radiometer follows. Okay, so for our short-term 2 to 5 year project, the idea was to start with the Rydberg sensors or gravity radiometers. So it's kind of two technologies that are have a lot of interest, and look at some ground-based or airborne experiments and applications in the water cycle, and also maybe in terms of the Fourier transform spectrometers, look at measuring these greenhouse gases as technologies that are relatively far along.
Thank you again for all our leads and for giving their great summaries. I'll just add that all of these notes will be compiled and it'll go into our overview workshop document and publication. So with that, we'll actually, before we begin our next session, we're going to have an overview talk from Professor Tim Palmer. So Professor Tim Palmer is a world-renowned atmospheric physicist and Royal Society Research Professor in Climate and Physics at the University of Oxford. Originally trained in general relativity, he transitioned into meteorology at the UK Met Office before making landmark contributions during his tenure at the European Center for Medium-Range Weather Prediction. He pioneered operational ensemble prediction techniques, fundamentally transforming weather and climate forecasting by accounting for chaos and initial condition uncertainties. His research on stochastic parameterizations and high-resolution Earth system modeling has significantly enhanced early warning systems for extreme weather events and long-term climate projections globally. Recognized as a leading global authority on nonlinear dynamics, he has served on major international scientific committees and contributed extensively to the assessment reports of the IPCC. So with that, I'd like to welcome Professor Tim Palmers, who will be giving a virtual presentation.
Okay, look, it's a great pleasure to give this talk. I think it's the first time I've given a talk at a CLIVAR meeting for quite a few years. I was the chair of the International CLIVAR SSG back many years ago now, 2006, 2009, with Jim Hurrell. I've actually been working with Jim very recently on a National Academy report on extreme weather attribution. So I encourage you to look at that. But most of my career has been in weather and climate modeling, but I did a PhD at Oxford in quantum gravity and general relativity. So I have some knowledge of quantum mechanics. So if I could have the next slide. I'm going to talk about a couple of papers, mostly the one on the left in BAMS on quantum computers, which I wrote with my then postdoc Felix Tenney. I think I saw that Felix was on the call here, so he can answer any questions that I'm unable to answer. And a more recent paper in PNAS, which I'll only talk for a minute or two, but it's a more speculative idea. The motivation for writing this BAMS paper was basically somebody came up to me once and said, or a colleague in the atmospheric physics department at Oxford, so when's somebody going to write a Fortran compiler for a quantum computer? Because I can't wait to use these things. And it occurred to me that, most people do not have a very good understanding. Climate and weather modelers do not have a good understanding of quantum mechanics. And there are some, well, as I'm sure everyone knows, there are some really important conceptual differences between quantum and classical computers. So this talk, we call it the good, the bad, and the noisy, to try to bring out some of these good points and bad points about quantum computing. So if I could have the next slide, please. Well, the kind of good point, the main, I suppose, issue that makes quantum computing attractive is that when you have n qubits, everyone knows that the qubit is the kind of equivalent of a bit for a classical computer. And when you have n qubits, the state space available to you grows exponentially with n, unlike in a classical computer where it would kind of just grow linearly with n. So a typical n qubit state, expanded in the basis, some sort of basis for these n qubits, would have these 2 to the power of n complex numbers describing the various amplitudes. And if you say took n equals 30, which is not these days is not an especially big quantum computer, that gives you available to you a state space which has dimension 2 to the power 30. So that's as big as a weather forecast model. So if you can get some algorithms with an exponential advantage, that's a good thing. But even without that, it just means that you have available to you the number of degrees of freedom as you would have with a very big classical computer with just a 30 qubit computer. So that's kind of, if you like, in a nutshell, that perhaps the single most important thing that makes quantum potentially interesting and potentially advantageous. Could I have the next slide, please? And as I noticed that you've already discussed this to some extent, but we're dealing with nonlinear equations. Now, at first sight, you might think, well, if everything's governed by the Schrödinger equation, which is linear, then solving nonlinear equations is going to be problematic. But actually, that's not the case. And we actually did some work, Felix and I, with Seth Lloyd from MIT, who's a real expert in quantum algorithms, to look at how we could solve nonlinear differential equations on a quantum computer. And we described that in the BAM's paper, and we illustrate it with a very simple kind of logistical equation. The idea, though, is to code multiple copies of a quantum state and let these copies interact via an interaction Hamiltonian. So the nonlinearity is encoded in the interaction Hamiltonian. I've spent a lot of my career working with the Lorentz 63 model of chaos, just the 3-component model. And I've always felt that that's a good kind of starting point for any sort of investigation of a sort of chaotic system like weather. So we did have a look at this, the algorithm in a practical way. You know, how if you wanted to integrate the Lorentz equations for, you know, this is 100 integration steps, you know, how many qubits would you need? And the estimate was around 1,000 in total. So that puts a bit of a damper on this. So it means that already, when you've taken into account all these multiple copies and various other issues, you're at a level of qubits where, well, you know, we're still waiting for a quantum computer that big. So I kind of would agree with the summary session prior to my talk referred to the bottlenecks of nonlinearity, and I think that's still, I would say, an issue. Something I haven't seen discussed is kind of the measurement problem in quantum computing. I mean, you can do all these kind of unitary transforms to sort of try to mimic things like the nonlinearity of Navier-Stokes. But at the end of the day, you've got to get the information back out of the quantum computer. And there is no kind of equivalent of just write X or print X on a quantum computer. You have to measure the wave function, basically. And I like to think of it, when I talk to people, I like to think of it in terms of the game 20 questions, where you have an object and you want to know what the object is. You have to ask somebody questions about the object to get information back. But the questions you can ask are questions where the answer is yes or no. So you can ask, you know, is it a piece of fruit or is it colored orange? And these questions correspond to the basis in which you measure each of the qubits. And a qubit, if it's a spin or something like that, you measure it, and in that basis you get the answer up or down, which corresponds to yes or no. I mean, if you design the basis carefully, and that's kind of half of the art of quantum algorithms, to come up with a clever basis where when you do a measurement, the answer yes or no really does give you useful information, because most of the time an arbitrary basis will give you an answer yes or no, but the nature of the quantum measurement problem is such that only tells you a probability of something. But if you're kind of really clever and you find good bases to measure your quantum state, you know, the answer yes or no can give you some, you know, really definite piece of information. No, the object is not a piece of fruit, for example. But the bottleneck comes in the fact that you can only ask as many questions as you have qubits in your quantum computer. For each run, you do a run, you have some kind of output wave function that you want to measure, but you can only have these n is 30. You only have 30 yes/no questions that you can ask the quantum state. And once you've asked those questions, that's it. You've got rid of the information has been destroyed. There's no more questions you can ask. Now, I would just kind of contrast that with going into a weather forecast office, and you see on the various monitors and things, you know, forecast cloud fields and forecast precipitation fields and wind fields and so on. And it may be from, you know, multiple ensemble members and all sorts of things. You've got kind of gigabytes, terabytes, I don't know, of data just continually being displayed and whizzing around. And the forecasters, you know, they use that information in making the forecasts and tailoring forecasts for specific users. So you have to contrast that with a quantum computer where you've just got these basically n bits of information, and that's a massive, you know, reduction in what you can actually access. And so this, for me, is one of the, I mean, I'm kind of agnostic about the nonlinear problem. I mean, at the moment, it seems very difficult, but of course, you can never know somebody may come up with a better algorithm than the one that Seth Lloyd and Felix and I came up with. But this thing about output is really quite a fundamental problem, because it's the nature of the measurement problem in quantum mechanics, and I kind of don't see a way around that. So I'll leave that as a bad point. So the next slide, please. I've been a big advocate for many years now of making our classical weather and climate models stochastic. I mean, this began at ECMWF back in the 1990s, where we developed an ensemble prediction system for weather, and it was clear that just the initial condition uncertainty wasn't sufficient to give a reliable probability forecast. So we needed some representation of the model uncertainty, the uncertainty when you discretize, the Navier-Stokes equations on a finite sized computer. And the technique that we developed, this is with Martin Miller and Roberto Buitza, was to make the subgrid parameterizations stochastic, so actually to introduce noise into the system. I mean, this had an immediately very positive impact on the probabilistic skill scores of the ensemble. And then later on, we looked at the role that this noise could play in actually reducing some of the systematic errors in models, climate models. So the biases, if you have a nonlinear system and you apply noise, you can see that the mean state and the climate statistics can change with the noise. Even though the noise is sort of symmetric, the nonlinearity gives you a rectification effect. And just for example, if you add noise to the Lorentz 63 model, so you might imagine naively that it would just blur the attractor out, but it does the complete opposite. It actually makes the regimes sharper. The regimes, the two butterfly lobes in the Lorentz model, can become considerably more persistent and long-lived with stochastic noise. And that, incidentally, is one of the major systematic errors to this day of climate models, that they don't persist the weather regimes like blocking anticyclones and so on sufficiently long compared to reality, which is incidentally a point that we made in the report with Jim on extreme weather attribution. I mean, like now in the UK, we've got a very long-lived blocking anticyclone, which has literally brought drought conditions to most of the UK. But in trying to assess whether greenhouse gas forcing has made these anticyclonic conditions more or less likely, it's very difficult to say, because the models don't do a good job in simulating long-lived blocking anticyclones. So you can't just simply look at a model and increase the CO2 and say, okay, has it increased the likelihood of season-long blocking anticyclones, because the model doesn't have it. Anyway, sorry, I'm deviating from the theme now, but I want to say the point about noise is that you shouldn't consider it necessarily as a bad thing. And the fact that the qubits in quantum computers are noisy conceivably could be used to some advantage. And again, I would very strongly advocate looking at the Lorentz 63. Can you integrate it on noisy quantum computers? Can you emulate how the classical Lorentz equations behave when you add noise, which, as I say, is to increase the persistence time of the two regimes? I mean, that would be a really interesting experiment, I think, on a quantum computer to see if you can do that. So I'm just making this point that noise is not always your enemy. It can be your friend, and that's about it. So I've got a few minutes left. So can I have the next slide? Yeah, it's not impossible that algorithms for solving Navier-Stokes will be found, but the evidence to date is we'll need very large numbers of qubits, and something as simple as Lorentz 63 needs 1,000. So let's call it an open problem, but I don't know. I'm not 100% optimistic. The noisy aspect of quantum computers could be put to advantage. That's an interesting problem, I think, and I'd encourage somebody to look at that if they have time. The output problem or the measurement problem is a real fundamental issue. There are some hybrid applications of quantum computers. I mean, if you have a a branch which depends on something being true or false, well, that's a very, that you only need one bit to know whether it's true or false. So maybe there's something there. On the other hand, I don't know. I don't see those branch points as being especially computationally sort of challenging. So I don't know whether that's a useful thing or not. Oh, and the one last point I wanted to make is to say that I hope Felix Tenney, my ex-postdoc, gets a chance to speak at this workshop, because he has some interesting ideas in using quantum for AI sort of weather prediction. And I'm kind of agnostic about that. Felix has explained it to me a couple of times, and I kind of get it, but I'm not 100% sure. But I think it's an interesting area to pursue. The only thing I would say is I feel very strongly indeed that we'll still need physics-based models for climate, for looking at outer sample issues. So I don't think this kind of quantum for AI will solve all the problems that we need for climate forecasting. I'm really interested in quantum mechanics because of this problem of how to couple it to gravity. That was my PhD problem, and I'm kind of returning to that in a sort of post-CLIVAR, post-climate modeling career. And the paper, I just want to talk very briefly, because there's a reason why quantum computing might not work at scale, and that's because quantum mechanics itself might fail at scale. So I've been developing a theory. Could I have the next slide? I'll just say it in a few words. This is just for your amusement, if you like. The axioms of quantum mechanics were formulated by John von Neumann, and the first one, the most perhaps important one, is that the quantum state's an element of a Hilbert space, so this vector space over the continuum field of complex numbers, and I've stressed that word continuum for a reason. The observables are Hermitian operators, so the things that we can end up measuring are Hermitian operators. They define the bases. And then we have this really kind of weird thing called Born's rule, which I say it's weird because it's an axiom which tells you how to kind of get observational probabilities from the amplitudes of the Hilbert vectors. For me, it doesn't make sense as an axiom. It's too bizarre. It reminds me of what Isidore Rabi said when the muon was discovered back in the 50s. He said, who ordered that? And Born's rule has that similar flavor to me. I mean, sort of, where on earth did that come from? So could I have the next slide? The paper I published in PNES earlier this year is an attempt to formulate a theory of quantum mechanics where you kind of get rid of the continuum. In classical physics, it's quite easy, by the way, if you can take, we do this all the time, solving Lorentz 63, which has a continuum time derivative. You can discretize it, and from theory that if the discretization is fine enough, then you'll get the classical, the continuum limit rather. But quantum mechanics is not like that. You can't do that. If you start discretizing Hilbert space, you're in something completely different. And this is an attempt to say what would be different if Hilbert space was discretized. There's something slightly ironic, by the way, because the word Hilbert space, or the phrase Hilbert space, was coined by von Neumann. Hilbert was his mentor, and he kind of coined the phrase Hilbert space in respect for his mentor. But Hilbert himself said very clearly that the infinite is nowhere to be found in reality. Of course, if you have a continuum, then you have infinitesimals, and so 1 over infinity plays a key role. So there's something ironic there that the space that von Neumann named after Hilbert himself probably wouldn't have approved of. And then John Wheeler, who was also a critic of quantum mechanics, criticized the continuum, and he said it concealed the information theoretic nature of the wave function. So could I have the next slide? So I formulated this thing called rational quantum mechanics. I'm not going to go through. I mean, there are a number of reasons why it's simpler. It only has one axiom. Born's rule is emergent. The information theoretic nature of the wave function is made explicit. It solves the measurement problem. It solves Bell's theorem, which is about spooky action at a distance. Could I have the next slide? The point is, I just want to make this point that there's a prediction from this theory, which is relevant to this workshop, which is that when the dimension of Hilbert space becomes so big. So big means 2 to the power, roughly 400, 2 to the power 400. So the Hilbert space of 400 qubits. Then in this, then you start to feel this discretization, and you can't even allocate one classical bit of information to each of the 2 to the power 400 Hilbert space dimensions. Now, when that happens, I mean, if it happens, so it'll only happen if this theory is correct. But if it happens, the quantum Fourier transform will start to fail as an algorithm with a quantum advantage, and anything that depends on the QFT will fail. So Shor's algorithm will fail, and in particular, then all these encryption algorithms will start to fail, or the quantum advantage will fail. So insofar as a classical computer will never be able to factor a 2048-bit RSA integer, neither will a quantum computer. The exciting thing, according to the people who work in the quantum computing industry, is that they think this should be testable in a few years, perhaps as few as like by 2030. So this last point I'm just saying for amusement, because it's very speculative, but I just kind of raise it that it may be the case that although quantum mechanics and quantum computers work very well for small numbers of qubits, they may actually start failing for large numbers. Anyway, that's my speculation. So if I could have the last slide. If I put this all together, I think if I'm honest, I would say I'm skeptical that quantum computers will be useful for operational weather climate prediction models with physics-based models. As I say, they may well be useful for more AI-based applications. I don't know, but for the physics-based models, I think the bottlenecks of nonlinearity, but also this kind of the bottleneck of the output is so severe. I just find it hard to believe that they will one day be useful. It's conceivable that there may be niche applications, and that some sort of hybrid quantum classical computer may be achievable. But I think once you start talking these hybrids, it becomes, I mean, the whole classical algorithms in computational science are so unbelievably well optimized that once you start introducing hybrid operations, that itself introduces big bottlenecks at the hybrid interface. So that's my overall conclusion. I mean, good luck with the people that work on this. And I really encourage people to look at something like Lorentz 63, because it's a great test model of something that's obviously much simpler than weather, but carries the nonlinear chaotic aspect of it. And with the remaining minute or two, I'm happy to take any questions. Thank you.
We have a few minutes for questions.
Hi, Tim. Thanks for the excellent talk. I have a question on your conjecture on quantum computers will fail to assign even a single bit information. So what's your opinion on quantum error correction, which uses large number of noisy physical qubits and run a protocol and try to encode less information using redundancy? So do you think, where does that fit into your conjecture?
Yeah, right. So, I mean, it's this difference between, what are sometimes called logical qubits and physical qubits, to get the equivalent. So the calculations I did in that paper of where this sort of discretization start to become important is around 400, but that's 400 kind of logical qubits. So with error correction, we'll need many thousands of physical qubits with all the error correction and so on to get the equivalent of 400 logical qubits. So, I think the way I would say it is like this, that just very, very crudely speaking, if you had 400 logical qubits, you could probably factor a 400-bit integer. If you had 2,000 logical qubits, you could factor a 2,000-bit integer. That's not exactly correct statement, but it's roughly right, let's say. So my point is that the industry standard for encryption are these 2048, so 2,000-bit integers. So you see, that's so far above 400 that it kind of doesn't matter how many physical. If you had 1 million, you might have 1 million physical qubits, which would in principle give you more than 400 logical qubits, you might have a few thousand logical qubits. If you had 1 million physical qubits with error correction, and it provided you with, say, a few thousand logical qubits. My prediction is that the algorithms, like Shor's algorithm, for those several thousand logical qubits will fail because of this information restriction. Now, this is, I just emphasize this is a consequence of a theory which I have proposed, which discretizes Hilbert space. So in a way, I don't want to say I'm right, because I don't know. I'm just saying this is a test. This will be a test. I actually think, for me, this is actually probably the most exciting area of quantum computing, that it may be able to test fundamental theories of physics. This is basically the idea here, that you're testing some idea, the continuum, that say people like John Wheeler were saying for many years when he was alive, that the continuum assumption in quantum mechanics is wrong, and that and this may be the first occasion where we can test the experimental consequences if Wheeler was right. Yeah.
We have an online question from Xiang-Yu Li.
Yep.
Hi, thanks for the thought-provoking talk. So my question is that, first of all, in terms of the continuum in quantum physics, like in which picture Schrodinger's equation or Heisenberg's interaction picture? And the second is that what's the relation between the new theorem, the rational quantum mechanics, and the many world interpretation? Because we sort of have a consensus that we could basically test this many world interpretation on a larger scale existing quantum computer as well. So I wonder if there is like a converge towards that end.
Well, I just want to emphasize, so the answer to the first question, it doesn't matter. Both the Schrodinger equation and the Heisenberg equation, the Heisenberg formulation and the Schrodinger formulation of quantum mechanics, they both depend on the existence of this Hilbert space continuum. So they both, so it doesn't kind of matter, either of them. As far as many worlds, many worlds is one interpretation of quantum mechanics, and there are many other interpretations, the Bohmian interpretation, the Carlo Rovelli's relational, I don't know. There are kind of many interpretations. I don't think there is any. The nature, like last year was the 100th anniversary of Heisenberg's paper, and Nature, the journal Nature, did a kind of survey of all these interpretations, and it's clear there is no consensus amongst the quantum community about which is the right one. My answer to this is none of them are right. None of them are right, because quantum mechanics isn't right. And for me, the bell, and going back to the original EPR Einstein-Podolsky-Rosen paper, it makes it very clear that quantum mechanics is incomprehensible. As it's a very accurate theory, but it's an incomprehensible theory. And this rational quantum mechanics, I've just stressed this experimental test, but it makes quantum mechanics much more comprehensible. You can understand the Bell inequality without having to invoke spooky action at a distance or anything like that. So, but the important point is it's not another interpretation of quantum mechanics. It's a different theory to quantum mechanics.
Yeah, thanks. I'm looking forward to read the paper.
All right, let's thank our speaker one more time. So now we'll start the first session of today, quantum algorithms for differential equations. So determining if and how quantum computers can be used to solve differential equations arising in weather and climate with an advantage over classical machines is still very much an open problem. Fundamental questions need answering, like, can quantum computers solve nonlinear differential equations with advantage? Can we prepare interesting initial conditions, or are we relegated to kind of purely idealized states, which we can only evolve those forward? And also, what useful information can we read out from the quantum state? And obviously, many, many more questions. So in today's session, we'll be exploring some of these topics.
So thank you for the nice introduction, and also thank you for the opportunity to present here. So I'm Kazumasa Ueno from the University of Tokyo, and today I will talk about the quantum linear system algorithm for the two-dimensional radiative transfer equation. So the target equation is this steady state radiative transfer equation. So it is the equation about the radiance I, and it contains the streaming and extinction and emission and scattering terms. And there is no time derivative terms. This is justified by radiative process is much faster than the atmospheric process that determine the optical properties. And the key properties of this equation is that this equation is linear in radiance I, and so coefficients fixed by the atmospheric state. But this is a very large system equation by discretization because it depends on the spatial grid points and also the propagation direction. And here we discretize this equation using the discrete ordinates method for the angular resolutions. And this reduces to large sparse linear system. And U equals F with the dimension size n is the spatial grid point times the number of discrete angles. And U is the vectors that gather the radiance, each radiance. And F contains the emission and boundary sort terms. And here I mentioned the relation of the previous research. So there's also presented in the yesterday's talk, but there is a previous research that mainly based on the time matching approach. So they are focused on the time-dependent radiative transfer equation and utilizing quantum lattice-Boltzmann method to solve them. But it requires cost for proportional to the number of time steps. On the other hand, in our approach, we first focus on the steady state radiative transfer equation, solve the linear system equation using quantum linear system algorithm. And here, specifically, we use the quantum singular value transformation to the linear inversions. So here's the brief overview of the quantum singular value transformation matrix inversion. So this approach is also introduced in the previous talk. And we utilize the block encoding because the coefficient matrix A is not unitary. So we utilize block of the A over alpha for the encoding of the unitary matrix. And we also utilize the answer qubits to encode this. And then we the quantum singular value transformation transforms the singular values of the original matrix using the polynomial functions. And if we take the polynomial function as an approximate of inverse function, we can operate the inverse function inverse of the original matrix A. So, but originally the inverse function diverges near the zero, like this figure. So we have to approximate in some ranges far from zero. And in this algorithm, the polynomial degree is related to the cost of the quantum algorithm. Relation is like this equation. So if we want to approximate the inverse in precision epsilon inf, we need this dQSBT polynomial functions. And here, the kappa QSBT is the parameter that relates to the original matrix, and we utilize the kappa effective for this matrix. This is the smallest singular value of the original matrix A over alpha. And in order to estimate the resource required in our quantum algorithm, we focus on the two metrics. So one is the solver core cost. This is cost for solving the original linear system equation and then obtain a solution in a quantum state. And this can be written in using the polynomial degree D and the number of gates required for the one block encoding. And also, we estimate the end-to-end cost for including the extraction of the observable, and it requires more times than repetition count written here. And in this research, we estimate the couple effective by measuring numerically for the this discretized RT system. And also, we built the block encoding of matrix explicitly. And also, by estimating the observable overlap and target precision, we can determine the repetition count. So here I show the problem setup of our quantum algorithm. So we focus on very, very simple problem setting. So we consider the rectangular two-dimensional space that one axis is horizontal and one axis is vertical. And we have the solar radiation from the top boundary, and we suppose that the lambation reflection surface. Horizontal direction, we assume the periodic boundary condition. And also, the important assumption is that the cloud is fixed in a rectangular region around this. And also, the optical properties are constant in the cloud region and the clear regions, like using these properties. And we utilize a phase function, Henyey-Greenstein phase function for in-cloud scatterings. And we utilize the nice structure of the original coefficient matrix for the block encoding. So the original matrix has mainly two terms. One is scattering terms, and the other is streaming terms. And scattering terms are coupled with different directions, and it appears as a block diagonal form in this matrix. And streaming term is only appear in the adjacent cells, so it's not depend on the number of spatial grid points. And we utilize a sparse access oracles for the block encoding models. So in this model, we need two types of oracles. One is index oracle that is input the index of low index using the Kalman index and also entry of the non-zero values. This can be achieved by reversible index arithmetic, modulo plus minus one other for the streaming terms, and controlled swap weights for the scattering terms. And we also utilize a value oracle that encodes the matrix value in the quantum amplitudes. And this can be achieved by using controlled RY rotations, and that is the controlled bits is based on the direction pairs and the cloud flux. So we assumed that because we assumed that the cloud properties, optical properties are not dependent on the spatial dimensions, spatial grid points. So no gates, no need to apply gates cell by cell. And here I show that validation results that is calculated state vector simulation. So this shows the downward flux of the shortwave settings. And the left panel shows the classical results, classical direct results. And the middle panel shows the our quantum algorithm results. And the right panel shows the difference of these. So in this setting, so we set the couple QSVT as 5,000 and polynomial degree as 35,001. The relative error of this problem is about 0.16% for radiance and 0.13% for downward flux. And then let's move on to the resource estimation. So first, estimate the effective condition number for this RTE matrix. So in the left panel, effective condition number, different grid number are plotted. In the right panel, couple effective for different angular resolution are plotted. So from this, the dependence on the number of horizontal grid points is relatively low. It's almost constant compared to the increase of number of vertical grid points and the number of discrete directions. And then I show the block encoding cost of UA. So the left panel shows the one-axis extension, and the right panel shows the extension for angular resolutions. And the orange line shows the topology gates, and the blue line shows the RY rotations. They are the only non-Clifford gates appeared in NARC block encodings. And from this result, the dependence on spatial grid points is very weak compared to the dependence on angular resolution. And integrating by these two results, we can estimate the solver core cost and also end-to-end readout cost. So the blue line shows the solver core cost. So that is the cost for obtaining the radius vector as a quantum state. And the orange line shows the end-to-end cost for estimating the top of atmosphere average flux, horizontal average flux for 1% error. So the scaling for the horizontal grid points is favorable in this graph. And the dependence on angular resolution is much higher in these three. And the number of T count, so we have converted the non-Clifford gates into a T count using some metrics. And so the number of T count is about 10 to the power of 10 around for the solver core cost, and 10 to the power of 16 for the end-to-end cost. So it's much relatively higher for the practical quantum algorithm, like for the quantum chemistries. And then finally, I show the logical qubit requirements. So the logical qubit requirements is favorable. It is in our problem setting for these great numbers. They are less than 100. So they don't exceed 400 for the promises. So it is very, very favorable result for our algorithm. So here's the scaling summary and take-home message of our my talk. So the extending the horizontal grid is computationally cheaper in our problem setting, but however, the end-to-end cost remains still high. It's about 10 to the 16 T gates. So even at these small problem sizes, so this is a point. And finally, I appreciate the help for all the help for my research. Thank you.
Thank you so much, Kazumasa. That was a great talk. I have some questions for you. So next, I'd like to welcome Hsuan-Cheng, a PhD student from Pennsylvania State University, to give his talk titled Quantum Simulation of Differential Algebraic Equations with Applications to Unsteady Stokes Flow.
Hi, everyone. I'm Hsuan-Cheng. I'm from Penn State, and my advisor is Xiang-Yu Li. And thanks for the invitation here. So I'm going to talk about quantum simulations of differential algebraic equations. So we are going to discuss what's differential algebraic equations and the techniques we're going to use, for example, dilations and quantum Zeno effects. And then last but not least, the applications for like some electric circuits and some fluids dynamics like Stokes equation. Okay, so why differential algebraic? So we may discuss what's a differential algebraic equation. So of course, it's going to be a differential equation, but then we're also going to have an algebraic constraint. For example, like time derivative of x of t equals to a matrix A times x. But then we have an extra algebraic constraint, like let's say matrix C times x equals to 0. And this is a differential algebraic equation. Okay, so like for example, singular perturbation limits naturally leads to DAEs. Like we can see the right-hand side graph here, a van der Waals equation from Hare and Wanner textbook. So when the parameter tends to 0, we can set it to a reduced problem. So we can solve it more easily. And then there's also in physics world, there's some Bridget constraint also leads to DAEs. For example, transistor amplifier with 5-node voltages. So the constraint is the total current equals to 0. And also some multi-body mechanisms and some Cartesian pendulum as well. So these are just simple examples for the DAEs. So why don't we darkly solve the DAEs on quantum computer? Is because normally we need to have a Schrodinger-like equation, so I times a state psi, time derivative, of course, equals to a Hamiltonian h times psi of t. But now we have two equations. One is the x prime equals to Lx plus, sorry, there's a typo there, is Lx plus c dagger times Lagrangian multiplier lambda. And our constraint is Cx equals to 0. So this may not be compatible to quantum machines. So we need to first have a bridge to map it to a Schrodinger-like equations. Then we can do the time evolution. Okay. So now we are going to discuss about the dilation techniques, or you can say like Schrodingerization. And I think previous talks has a little bit include about this. So the problem is L is not unitary, but we can decompose L into negative IH plus K. And now H and K are both Hermitian. And you can introduce an Azela Hilbert space H of A, HA, but the problem is now we are not going to say it is just putting one extra ancillas. We may use many more extra ancillas. And we define this H hat to be I identity in the Hilbert space, ancilla Hilbert space A, tensors with original Hamiltonian H plus IF tensor K. So this F is just some skew Hermitian operator that we can pick on our own. Okay. So in the dilated space, we have our new state I times psi time derivative equals to H hat times psi of t. And then after we do evolution of this, we can map this back to our original vector x of t by using some functional mapping. Okay. And we also use this dilation techniques for linear SDEs as well. So we know SDEs is not directly compatible to quantum machines as well. So we first map this linear SDEs to a stochastic Schrodinger equation. Then we can use some trajectory-wise simulations or like Lindblad simulations to get the quantity we want. So this is the QR code of that paper. If you're interested, you can take a look at it. Yeah. So after dilation, we wonder what is quantum Zeno effect. So basically, it is saying we can do this projection in many short steps to prevent its running out of a subspace. So you know the differential algebraic equations, we have a constraint, so which means we probably need an orthogonal projector to keep mapping it back to the subspace that satisfies this constraint, okay? And we have a formula here is when n tends to infinity, then this p times e to the power negative iht short time t times p equals to e to the power negative I ph p long time t times the orthogonal projector. So this thing gives us two methods to simulate this differential algebraic equation. One is we can directly just simulate the right-hand side equation. So we can just simulate this php and then times the orthogonal projector p, or we do it many short time steps and repeat it. And in our work, we focus on the right-hand side technique, so we just directly simulate this e to the power phpt. Okay, so the overall summary of this project Schrodinger dynamics is we have original variables x of t, so x prime t equals to Lx plus c dagger lambda, and the constraint is c times x of t equals 0. We use dilation to map it to psi of t and d psi of t. Now the constraint d psi of t equals to 0. But now this is still two equations, but we know we can project it into a single equation that I times psi time derivative equals to p times h hat p psi of t. This h hat is the dilation of the original matrix L. So I think I discussed it before. So this p needs to be an orthogonal projector. So we know it is in form of I minus d dagger times d dagger, d times d dagger inverse d. So when you do it on the quantum circuits, you need to do QSVT for this matrix inversion D times D dagger. So which is going to cost us some more, and I'll discuss later. And eventually, we focus on our original state x of t, which can be recovered by this bra L tensors with identity times our dilation state. And this bra L depends on what dilation technique we use, as the Hilbert space, what Hilbert space we pick, but it's on your own. So assume we have the access to blocking code of the L and C, and then we need to use QSVT to build a projector P. And then we simulate P times H hat P at state time T, okay? So what's the overall cost is, first of all, is if you want to simulate P times H hat P, then this thing, the Hamiltonian norm itself is going to give you a fixed cost, the norm of H hat. And then we know to build a projector P, we need to use QSVT. So the spectrum gap is going to cost you as well. I think previous talks also include this. And of course, the initial state preparation. And after that, we have post selections. Those also going to contribute some complexity cost. Okay. So the first application is just a simple ladder circuit. So I'm not going to give too many details here, but we can see for some fixed constraint, we will have the matrix L and matrix D. And then we know we can build a projector P by using I minus this D dagger times D dagger inverse times D dagger. And for this example, we know our L and H hat will be fixed O of 1. The norm is bounded by a constant because there's no grid size and it's just a fixed matrix. So the overall complexity for simulation is O tilde of T. This tilde, O tilde means we suppress all of the extra logarithmic factors, okay? And this overall complexity is just saying the simulation itself is not saying about preparation and after all. It's just about the evolution, okay? So the second application is incompressible Stokes flow. So in fluids dynamics, we focus on Navier-Stokes. And Navier-Stokes is a nonlinear equation. So we start with a linear problem, Stokes flow. Okay, so we know in continuous form, it is partial time derivative u minus Laplace of u plus gradient p equals to non-homogeneous term f, and the divergence is 0. And we need to discretize it so we can put it on a quantum machine. We can use either staggered grid, for example, Markov and Sill techniques, or mixed finite elements to get a semi-discrete system, which is also a differential algebraic equation. So we have the mass matrix MV times UH prime equals to LHUH plus DH dagger times P of T. And this DH times, I think there's a typo, U of T equals to 0, okay? And we can see the right-hand side of this figure is just velocity and pressure after the discretization. But here, there's one problem is we know this LH is going to, the norm of LH is going to be scaled with the grid size h to power -2, which is, if you pick n grids, then it's going to be n squared. So, which is not a very good thing, but Stokes has extra structure, is we know this dTuh of t originally equals to like a projector P times Laplacian LH times another projector P times UH, right? But this Laplacian LH can be decomposed as Q matrix GH dagger times GH. So we know this SH, if we call this total thing SH, then SH equals to GH times the projector pi H itself dagger times GH times pi H. So it's like two matrix, like a dagger times itself. So we observe that if we use Gaussian dilation, then if we want to simulate this e to the power t sh, we can actually just simulate e to the power -i k bh here on the fourth line. And now this BH here is just scales with norm O of h to the power -1. So it's like O of. So this helps us from O of n squared to O of n. So this benefits us a little bit. But this is just for simulation step. For loading and post-selections and those preparations, we haven't included it yet. So maybe it's going to be more expensive. Okay. So we also give a numerical test of the dynations. If you can see in the graph, like if we do the refresh ancillus, then the dilation is still well maintained even in long time. And if we just do one-shot dilation, then the error is going to be large for long time, because after do dilation or Schrödingerization, it is going to be exact for infinite dimensions, but you truncate at finite dimensions. So you need to do dilations many times if the time is large. Okay. However, you can see on the right-hand side, like the pressure and velocity recover as well. Okay. So I think overall we can say the DAE constraints can be represented as the orthogonal projector map is back to the subspace. So we can use quantum Zeno effects. And dilation can map the non-unitary evolution into projective Schrödinger dynamics. And the applications include like circuits and incompressible flow. And furthermore, Stokes benefits from the additional square root structure of the Laplacian. And of course, natural next step is to include all the things like state preparations, measurements, and other applications. And of course, nonlinear problems like Navier-Stokes if possible. And below 2 QR codes are, the left-hand side is the work of this paper. And the other one is just the very recent paper we just published on arXiv. It's about the simulating wave equations on ion-trapped quantum computers. And if you're interested, you can scan. Thank you.
Thank you so much, Hsuan-Cheng. So finally, I'd like to welcome Dr. Nils Klement to the stage. He's from the German Aerospace Center, and his talk is titled Quantum Enhanced Convergence of Data-Driven Physics-Informed Neural Networks for Earth System Modeling.
Hello, everyone. So the approach of solving PDEs I'm going to talk about is a bit different from the ones we heard before, because here we're trying to use QML, or more specific physics-informed QML, to solve PDEs. And maybe the first question is, how do we physics-inform a network? So the idea here is that we are trying to use some kind of network, as shown above here. And the input to this network can be spatial or temporal coordinates, and the output of the network should be the solution or the approximate solution to our PDE. And in the first step, what we can do is we use boundary conditions, for example, initial conditions or spatial boundary conditions. And also we can include observations and objectives that we have for our PDE. For example, of course, climate data or climate observations. And this would be like a default regression task, right? What we also can do, or what we would like to exploit here, is that we can calculate derivatives of the network output, so the solution with respect to network inputs, so space and time, for example. And by doing this, we can calculate, as I said, the derivatives of the network, and we can combine these to the formulation of the PDE we're trying to solve. For example, here, Navier-Stokes equation. And by sampling points uniformly in our domain of interest, we can calculate whether in all of these points our PDE is fulfilled. And by minimizing this loss, so making sure that our boundary conditions and fixed data are fulfilled and our PDE is fulfilled in all of the collocation points, we can find approximation to the solution of the PDE we are interested at. Okay. Why is it a nice approach to do this? The method is mesh-free, so we do not need to discretize our domain of interest. So there's no discretization error. Of course, there's a different error. So it's of course an approximation to our problem. So instead of a discretization error, we get kind of an approximation error. And the solution is continuous and differentiable, which could be nice in some applications. In principle, we have unlimited data for the PDE loss because we can resample the collocation points during the training over and over again. Integrating multiphysics is quite straightforward. And also, as I said before, data integration is very easy because In the training data, you can just integrate observations and objectives and train your network based on this. And that also enables you to, typically called inverse problem, add trainable parameters into your network. For example, some parameters in your PDE, which are trained during training of the network, and you do not know the specific value for this parameter, but you can figure out this value during training, which can be quite nice. Also, you could add additional input, which can be this parameter in the PDE to your network, and this can give you a whole family of solutions to your PDE. So that's basically the advantages. Now, there are, of course, challenges, as always. Numerical solvers, standard numerical solvers, are, of course, optimized and validated, and they are very good. Resolving certain phenomena like shock waves, gradients, and turbulence is quite hard, because typically these networks have kind of an averaging effect, which makes representing shock waves and so on quite hard. There's like this accuracy I talked about before. So although we have no discretization, there's the solution is only approximation to the solution we want to obtain. So we can have an accuracy problem, which is also related to the slow and potentially unstable training, because the loss landscape of such a physics-informed neural network is oftentimes very complex, which makes the training quite hard. I brought an example. So as you can see, here the mean squared error is calculated by, so for a very simple example, is calculated by solving the problem numerically and seeing how the training of the physics-informed neural network, how the mean squared error compared to the numerical solution improves over training. And as you can see, it takes, in this case, 10,000 training epochs to get to a good solution. So yeah, it can take some time to find a good solution, even for simple problems. So what we're trying to do is use quantum machine learning here. The idea is, on the one side, that like the standard formulation of QML forms based, so this is this data encoding and trainable layers alternating, forms kind of a Fourier model. And by using reasonable data encoding for your data into this network, you can get quite an expressive circuit. And what you can find, so there are a lot of studies you can find in literatures. They show that using quantum machine learning for pins is, compared to classical approaches, quite efficient in terms of expressivity. So stating that if you give both of the networks, so classical and quantum machine learning networks, same number of parameters, you can get oftentimes a better result for the quantum machine learning networks. Or the other way around, you can use less trainable parameters in the quantum architectures to get to the same accuracy. So this is quite interesting. Now, what we did is to figure out how that works, and whether and for which application we can use that. We tested differential equations, in this case, parameterized differential equation. And by using different parameters, nonlinear or linear, which would correspond to Berger's equation or the heat equation, and also different scalings for the diffusive part in the equation. Also, what we did is use different number of trainable parameters and different numbers of data or collocation points during training. And that's basically our setup. We wanted to train to see for which setups and in which cases quantum machine learning can help in solving PDEs by using physics-informed neural networks. So the classical counterpart we are using is inspired or motivated by the classical studies I mentioned before. Usually they use a dense, fully connected classical neural network. And what we're doing here is, for all the different setups we are using, we're always doing kind of a hyperparameter tuning. That means we are testing all the possible depth for a certain number of trainable parameters and see which one's the best to kind of get the best classical fully connected neural network we can use for the PD we are considering at that moment. And the implementation is done in Equinox and JAX. Here the advantage is that we can use the same training pipeline for this word network and also for the quantum pin we're trying to train here, make it as comparable as possible. As I said, this is the quantum pin. What we are doing here is we have this quantum circuit in the middle, which consists of encoding layers and variational layers. And what we also do is we're using classical input and output layers. This makes sure that we do not have to stick to a certain type of encoding, but this encoding, which is done by the classical input and output networks, are learned during training, so that we hopefully get a very good feature map of the input data into the circuit. Yeah, and important to mention here, here we're using PNNL and state vector simulations, so no shot noise. The training I'm showing right now. As I said, what these classical input and output networks are doing is finding a nice basis to encode and and to decode and encode data in and from the circuit, and yeah, finally obtain a solution. Also here we did some kind of a hyperparameter study. First, we had a look at how many qubits to use in the circuit and how often to encode data into the circuit, because the more often you encode data into the circuit, the more expressive your circuit gets. But of course, your circuit gets deeper and deeper, which you typically do not want. For the number of circuits, at least for this setup, very simple setup we are using here, 3 qubits are absolutely sufficient, which is nice. Of course, it might change once you go to more complex problems. And the same is true for the encoding. Coding 3 times absolutely sufficient for this application. But again, for more complex problems, you might want to encode more often to get more expressivity into your network. And what's also interesting, what you can do is basically, if you give this network a fixed number of trainable parameters, you can either move the trainable parameters to the quantum circuit or move them to the classical networks. And this is what is shown below. So here we basically move the trainable parameters from the quantum circuit in the classical circuit to see what impact it has on the mean squared error we obtain after, I think, in this case, 5,000 training epochs. And as you can see, moving the trainable parameters to the classical networks leads to a decrease in accuracy. So this already shows that more quantum resources result in a better approximation of the final solution. Yeah, which is already nice to see. So in this case, the using quantum resources might make sense. So what we did now is, I've shown this before, like black curve you've seen before on the for the example I've shown. So this is basically the classical network, and training the quantum pin with basically the same setup. We reach a far better accuracy in less training epochs, which is of course nice. This is what we want to see. This is also an agreement with the studies I've mentioned before. So training for the same time, giving both of the networks the same number of trainable parameters, and we get a better accuracy with a quantum pin. But when we continue training for much longer, at some point the classical pin reaches the same accuracy as a quantum pin, which is interesting because I cannot make general claims, of course, but at least for the things I looked at here, the better accuracy is due to a better or faster convergence of the quantum pin compared to the classical pin. So the accuracy in the end is similar, but as I said, the convergence it's much faster epoch-wise, of course. So I'm not making any statements about like real runtime on any kind of real hardware. If you want to know more details, you can find, as I said, more details on the archive. I said it before, we did it for a lot of different setups. And this is basically the summary of all the setups. What I plotted here, the figure on top is the ratio of mean squared error after different training epochs. And what is quite interesting to see is that the convergence rate does not depend on which type of PDE we use or how nonlinear it is or whatever. It only depended on what the final accuracy is. So if you can, in the end, reach a very good final accuracy with both networks, the quantum pin tends to converge even faster than the classical pin. So a better final accuracy means also a faster convergence of the quantum pin, as I said, for the setup I used here. That's basically it for the moment. So as I said, what we observe is faster convergence for the setup we're using here. Of course, there are a lot of questions to be answered. I wrote down, I think, the 3 main questions that needs to be answered. Of course, there are more, but I think the first thing is what we are comparing here is the classical fully connected pin architecture with a quantum machine learning model. So far, it's not clear whether we see something quantum here or due to some, let's say, inductive bias of the network, because as mentioned before, this quantum pin is kind of a Fourier model. So maybe it might be meaningful to compare to Fourier feature pins and see whether, we can see some changes there or explain for what reason the quantum pin converges faster. So basically what this faster conversion is due to. And also, that is what I mentioned before, whether we can represent non-smooth solutions, because what we looked at right now is very smooth solutions, and how to incorporate or how to deal with non-smooth smooth problems is not clear yet. Yeah, and of course, the quantum pins we used here are tried with state vector simulations, so basically infinite shots and no other noise. And this is, of course, not something we expect in reality. So now the question is, how does this perform and how does this converge in reality? This is really one of the bigger questions, I think. And yeah, maybe also important prospectively is how does what I showed before scale, right? So we looked at a very small problem here, and what happens if we scale to more complex and bigger problems? Can this approach in any way be helpful compared to classical methods? Can we get any improvement on larger scales, or is it limited to these small areas? And what we've seen here is basically not enough to be compatible with classical numerical methods. Yeah. These are questions I can hopefully answer next time. Thanks.
Thank you, Nils. And now I'd like to invite all of our speakers back up to the stage for open discussion. So we'll take some questions from the audience. We can start in person if anybody would like to ask questions to our speakers. Yeah, please go ahead.
Hello, yes, I have a question regarding the differential algebraic equations. So we do have the AE solvers in our Earth system models now for our chemical reaction networks. So basically, hundreds of species reacting, and then the algebraic constraints come in, say, for the fast reactions, which can be approximated in quasi-steady state. So that's where the constraints come in. So we actually are using the AE solvers today in our Earth system models. So I'm just trying to get a sense, and I would mention also for those, the nonlinearity is quadratic. So, binary reactions, you have a quadratic system of ODEs. So I guess my question is general. I'm trying to get a sense of how practical, if I had a large system of ODEs like this, how many qubits when we go up to the nonlinear to linear, whatever methods, and is this an interesting use case, and is it actually practical at some point to attempt a DA solve for these systems? So
I'm not sure if I can answer this question correctly, because for nonlinear problems, even though it's not DAE, I am not sure how many qubits current quantum machines require to use. Like, for example, if you use Korner linearization, you have if you truncate in high n, it's going to take lots of memories because you have many duplicate tensor products. So I can't really give a direct answer about how many qubits you're going to use for nonlinear problems. Yeah.
I just remember our morning talk where I think the 3D Lorenz was hundreds, or at least with that approach. So it's hard for me to get a sense. Thank you.
Maybe I can add a little bit to that. So it depends on how, let's say you have quadratic nonlinearity, and I guess it depends on the truncation order that you would use after you do Carleman linearization. But let's say that I guess the minimum truncation would be 2. Let's say that you need let's say 2. It should go something like, if I call that as alpha, it should go and the system size would grow something like n power alpha, and the qubits would be log of n power alpha. It's not the qubits that's really going to be limiting you. It's really kind of encoding that matrix. And the Carleman matrix it's structured, but the structure is kind of tricky because it has all these tensor products that are not really not as nice and sparse patterns as you would have for your linear PDE discretization. The structure is just more tricky, and kind of just encoding that, and kind of the T-gate cost that you would kind of come from encoding that would really be your bottleneck.
We have an online question from Shan.
I want to ask for the QPINN. So have you tried for different PDE models that the accuracy of the quantum compared to the classical will be different, but it's more for different model. Have you looked at that? Some accuracy are better for certain kind of the model. What do you think that accuracy that compared to quantum and classical?
So let me repeat your question. So what you're asking is whether I would expect for different kinds of PDEs, the accuracy or the convergence rates should be similar. Is that correct? If that was your question. So I tried different PDEs, and so this PDE I showed before, which was parameterized. So I hope it covers several domains of PDEs, so to say. I looked at different PDEs, and for all of them, we were able to see similar things. But as I said, these systematic investigation we only did for this parameterized PDE.
Okay, we'll move on to the next question, unless Shan, you have any follow-ups. But if not, yeah, please, we have a question in the room.
So my question is, I had noticed on all the talks, there was this kind of recurrence theme that input and output bottlenecks were a big issue. And I wonder if, so you folks have been doing a lot of research on the algorithmic side from the quantum perspective. Do any of you have any thoughts on looking at the quantum algorithms and attempting to develop quantum inspired algorithms instead, where everything is classical, by looking at where is the quantum actually providing some type of an advantage? And this is open question. I mean, I'm not looking for a specific answer, mostly just your thoughts on this. I'm just kind of curious.
Yeah, no, I haven't really worked on quantum inspired algorithms, but that's a great question. I think these ideas of tensor networks are being really used in developing these quantum inspired algorithms. I think that's a really great place to do some exciting work. Yeah, I don't really have much more to add to that.
Yeah, I don't have so much clear idea for the dequantization of the quantum algorithm, and also there is a possibility for my radiative transfer quantum algorithm also could be dequantized in some sense, but I can't check, and I have to check for every cases for the quantum algorithm, I think.
Yeah, just a brief follow-up is I know NVIDIA, they're doing some hybrid and some quantum classical algorithms, and they're doing some work on it, so maybe you can check it out.
Maybe as a quick follow-up, maybe to make the question a bit more specific. So in each one of your use cases, where are you seeing the bottleneck of what you want to try to speed up be at? And maybe that might clear up a little bit where I was trying to get at. Is there a specific place where you're seeing that, okay, here is where we need a speed up, or maybe take advantage of the high dimensionality of the space? Maybe those types of ideas is what I was trying to get at.
So for my work, the Stokes equations, when you do discretizations, it's actually going to be mesh dependent. So it's eventually going to be how many grids, capital N to the power of something. So it seems like we may have an asymptotic advantage of for example, if it's 2D Stokes flow, and classically we use second order space and time discretizations, then classically it's T over N cube or something. And then, T times N cube. And then for our case, it's square root T times N square. So it's slightly better, but we couldn't claim quantum advantage just by having this speed up. Yeah. So eventually, for unbounded Hamiltonian simulation, and I think it's a bottleneck. Yeah.
So in our quantum algorithm for radiative transfer equation, the bottleneck is encoding the realistic atmospheric properties into the block encoded matrix. I already use the very, very simplified problem setting, but in order to incorporate the realistic atmospheric values, we need a cell-by-cell incorporation or some tensor network approximations. So this is one challenging point for my algorithms. And also extracting some meaningful observables is another challenge, I think, because in my algorithm, we targeted the top of atmosphere flux, average flux, but it already has a high computational cost. So it's important to find the meaningful but less computationally hard observable. is important, I think.
I mean, like you mentioned, like, data loading and measurement and readout, it's like the big challenge, right? Like very specifically in kind of the problems I've looked at in these Carleman linearized matrices, kind of encoding that using like a LCU style technique or just block encoding it. That was like a big challenge. And back when I started like kind of getting into this, and it is like kind of really interesting to like look at just how the solver works, like like QLSA or VQLS. It's just kind of understanding the working of that and kind of the benefits that would give. So if I just think of quantum algorithms just for doing like the evolution itself, I think there is like a big potential in like getting that like big speed up, because classically, like if you want to solve a matrix, I at least have to do one computation for every grid point. Right? So that already gives you a linear scaling. And if I can just bring it down to logarithmic with like quantum algorithms, that's a big speed up. But that can be killed at the loading and like the reading steps. And yeah, specifically looking at like this Carleman linearized matrices and how do you block encode it, that was one of the problems that I've been thinking about for a while. Yeah, and we used this linear combination of non-unitaries technique recently, a paper with Ruben and Tom and Amit. And so it's, yeah, looking at that problem.
Thank you. So in many of these differential equation problems, you invariably have to deal with unbounded operators. So the matrices that show up are essentially finite dimensional or finite rank approximations of unbounded operators. Is that something that you've encountered in terms of algorithmic challenges and like convergence issues and of that nature?
Yeah, sorry.
It's a general question for the panel, I guess.
I'm not really sure what unbounded operators are.
For example, differential operators where they are defined, say, on acting on a Hilbert space, but the domain is like not the entire Hilbert space, because like if you start taking derivatives you can have derivative sequences of functions in the Hilbert space that have unit norms, but their derivatives grow unboundedly as you apply, say, a differential operator, and creates all sorts of issues when you're studying convergence to the infinite dimensional differential operator. Is that something that you encountered in?
No, I haven't really thought about it, and I think it's a very interesting point. But
actually, I like unbounded Hamiltonian problems because we keep struggling with the condition number of the H, and I think one method that may help us is in real-world problems, the initial condition may be smooth. So when you apply with the Hamiltonian operator itself, it might maps it to a low energy space. So the actual eigenvalues pretty gapped. So there's a spectral gap. So actually we only need to focus on like small, two-sided eigenvalues. So which may give us some advantage on this. Like it's not going to be the worst case of the norm bound, operator bound.
We have another online question, so we'll do that one and then Anisha's, and then we'll break.
Yeah, so I have a question about this LCU, improved LCU approach. So could you please remind me why this complexity of the LCU is n times log n? Because the standard one developed by Nathan Webb and Andrew Childs, and later on its scales is polylog n. So why is it n times log n in the LCU?
Well, it's just for like the PDEs that I know we have looked at and kind of taking existing kind of like software packages to like compute the poly LCU. We just see that that's what the scaling is, that it's just even for sparse matrices, it still scales kind of linearly in like the matrix size. So it's more like that's kind of the empirical observation we got when like trying to do it. Ruben, if you have more thoughts.
Yeah, I guess it really depends. The scaling is going to depend on the specific system that you're looking at. And there's kind of two things that we look at when we're doing LCU. You're doing, you have a number of terms in your decomposition. And then each of those terms has to have some kind of circuit, and that circuit has to be efficient. So there's sort of like two metrics. And what I can say is actually for some of the LCNU work, which is really just another way to arrive at the LCU with an additional step, But for the LCNU work that I've done with Abinaya, actually the number of terms can be constant with your spatial and temporal discretizations, which is kind of amazing. It does scale with the truncation order. So we're doing like Kalman linearization work, but the number of terms is actually constant. Now, the circuit size for each of those unitaries does have a scaling and a dependence, but it's polylogarithmic with the spatial discretizations. So it's actually extremely efficient to do this LCNU approach for certain sparse structured matrices. Hopefully that's helpful.
Yeah, so you're saying that actually this like n times log n, that is like more like empirical observation from your simulation, or because I still can't understand like from the algorithmic framework, right? How would that be a n times log n, unless you consider some like a special block encoding factor that leads to n times log n?
I mean, I think like, even if you take like a very simple diagonal matrix, let's say, and you have a different value in each of your diagonal entries, I think like if you just run it, I think you would likely need like n entries and n terms in your LCU to like represent that. So I think that maybe at the extreme case of like a super sparse diagonal matrix, even that can need this linear scaling. Maybe that's helpful to think about.
Yeah, we can discuss offline because that would related to the sparsity S, right, in terms of the size of the matrix N, because that's where the quantum advantage kicks in, right? You would get a polylog N instead of N times polylog N. Maybe I misunderstood something.
Yeah, no, we can take it offline, but yeah, that is really what we were trying to get at. Like, we don't really want this linear scaling. I think for just doing poly LCU, like it, as far as I know, it scales from n log n to all the way to n square for dense matrices. So that's really the scaling. Just doing poly LCU, you cannot get to a polylog scaling in n. And that's what we were trying to circumvent with this LCNU technique.
Great, thank you. So Anish, with our final question of the session.
Yeah, thank you for all the excellent talks. I have a two-part question, I guess. The first one is based on metrics for truncation. You talked about Kalman linearization and Koopman operators as well, right? So when you decide about the truncation, do you also look at predictability metrics on how accurate these systems are in terms of the limit of predictability compared to the full system? And are you truncating where the predictability is close to the true system? That was one question. The second part was, are there applications of using machine learning based approaches to go to the latent space in the machine learning algorithms and then use the latent space as a reduced order representation of the system to then represent it on quantum computers?
I can take the Carleman question, but I don't really do machine learning, so I can't answer the next one. Maybe. So the Carleman, like I think you bring a very good point that like usually, as far as I know, how it is studied is just like the convergence, like as you keep increasing your truncation order, like what is the convergence of the Carleman linearized system to your true system? That's how it's done, and at least that's where we know the theory on. But I think you make a really good point that like maybe you don't have to do that, but maybe it's just certain observables that I'm really interested in, and like it's enough if I know how the convergence of basically the measurements and observables do. Like, yeah, that's a very good point, and I don't know if there is work that done on it, but that's you bring a very good point. I think that would really help a lot in like understanding or even reducing the truncation order that we would need if you don't really like care about the convergence of the whole system. Yeah.
Thanks.
So the question you were asking is whether QML could be used to reduce the order, basically.
I mean, even if not QML, just ML, where you take the latent space in the machine learning representation, right? If you have any kind of a machine learning algorithm that is emulating a true system, the latent space would be a reduced order representation of the system. Can that be used for like the quantum representation, which is what the Koopman or the linearization is trying to do, right?
I mean, so that's basically what I showed before, what these classical layers are learning, right? They're learning basically latent variables.
Yeah.
And these are, in that case, variables that fit well to this Fourier representation of the quantum circuit. I'm not sure to what degree that is applicable to other applications. So I think it, as always, it depends.
Let's thank all of our speakers one more time.
Welcome back. Our next section is on quantum algorithms optimization. And our first invited speaker is Dimitris Giannakis, who's a professor of mathematics at the Dartmouth College. Dimitris specializes in the intersection of operator theoretic techniques for dynamical systems and machine learning. His research on data-driven methods for coherent pattern extraction, statistical forecasting, and data assimilation have a wide-ranging application both in ocean atmosphere science as well as fluid dynamics. Yeah, it's my pleasure to welcome Dimitris for the talk. Thank you.
Thank you very much for the introduction. Thank you all for coming. It's great to be here. Okay, so I guess our story begins in the first few decades of the 20th century, where the foundations of modern ergodic theory, but also quantum mechanics, were laid out. And in ergodic theory, basically, instead of studying nonlinear dynamics directly, the general approach is to study them through their induced action on spaces of observables. So observables are quantities that we can measure about the system. So for example, temperature or circulation at particular locations in the Earth, that would be observables of the climate system. And if we have a nonlinear dynamical system acting on our state space, calling it here, so the state space of the system is X, and think of there is some evolution map that takes initial conditions from that space and gives us the time t solution. We want to study this map through the way it acts on spaces of observables. And these dynamics are generally highly nonlinear, but spaces of observables have linear structures. So they're like linear function spaces, meaning we can add together observables and scalar multiply them, and they have linear vector space operations. So as it turns out, the action of dynamical systems on such appropriately chosen space of observables is through linear transformations. They act through linear operators. And the main two objects of study in ergodic theory are the composition, or what is now known as the Koopman operator, and its dual, the Perron-Frobenius operator. The Koopman operator basically acts by composition of observables with a dynamical flow, meaning that it takes in an observable as an input and returns a new observable, such that if you evaluate that a new observable at some point, say X in the state space, it gives you the value that the observable takes at the state reached by a time t evolution starting from the point X. I'm showing here a pictorial example from an observable on the Lorentz attractor. This is the X coordinate on the attractor, how it is transformed under the action of the Koopman operator, where you can see that the development of these striations is basically the outcome of like sensitive dependence on initial conditions. But the transformation in this space of observables going from the left to the right picture, and unfortunately it doesn't seem like, is actually a linear transformation taking place in an infinite dimensional space of functions. And this approach has been quite instrumental in the study of dynamical systems from an analytical point of view. And more recently, there has been considerable interest in using this theory to develop various numerical modeling techniques, particularly data-driven techniques that leverage advances in areas like machine learning. Now, as it also turns out, this approach has actually deep mathematical connections with the theory of quantum mechanics. And in fact, this was recognized quite early. Some of the main developers in both classical and quantum mechanics had realized this. Koopman, in fact, in his paper from the 1930s, talks about transformations, unitary transformations in Hilbert space, very much with quantum mechanics in mind. And this, as we've already heard in different talks today, these connections are basically provide a promising route to building quantum mechanical representations of nonlinear classical dynamical systems, or also quantum-inspired methods that take advantage of some of the mathematical structure of quantum mechanics, but are implemented classically. And there are also related approaches we've already heard today. The Kalman linearization approach has some connections with Koopman operator theory. And climate dynamics, which is the focus of this workshop, is a important application domain that presents many challenges. We've heard that already from Professor Palmer's talk in the morning, but also there are, I believe, different types of opportunities where ideas and methods from quantum mechanics can benefit the field, and also we can hope that there are two-way interactions where questions from climate dynamics can inform new studies in quantum information science. So what I would like to do today is to try to give a description or an overview of how operator theory can be used as a sort of like universal or a unifying set, provides a unifying set of axioms that can describe both classical and quantum statistical dynamics as basically two different implementations of the same axioms. And using this unified approach, how we can leverage it to build consistent quantum mechanical representations of the statistical behavior of classical dynamical systems with certain favorable properties that occur in finite dimensional approximations, even without quantum computing, even with classical numerical, classical hardware. And I will use examples from data simulation of the El Niño phenomenon and closure of cloud resolving atmospheric models to kind of like highlight these methods. I'd like to thank my collaborators in this general work over the past year who are listed here. David Freeman was a PhD student and now postdoc at Dartmouth, is here in the audience and has a poster later on in the afternoon on some of this work. Okay, so since we're going to be dealing with quantum mechanics, well, one of the basic ingredients of defining a quantum mechanical system is a choice of an appropriate Hilbert space, and there are many choices in general, but I will be focusing on a specific one for the purposes of this talk, thinking that our dynamical system has some type of invariant probability distribution. Think of it as a climatology in the context of the climate dynamics, and our Hilbert space will essentially consist of observables, functions of the state, which are square integrable with respect to that reference distribution. Essentially means that they have finite variance. And for a general dynamical flow, the Koopman operator acts as a unitary operator on the Hilbert space. So this is already suggestive of connections with a quantum theory. And importantly, what the ergodic theory gives us, it gives us tools to approximate these operators empirically from historical observations or from, let's say, model-generated trajectories. In essence, we can compute matrix representations of the Koopman operator, so it's matrix elements with respect to the Hilbert space inner product as using empirical time correlation functions of observables. I'm not going to be talking about that today so much, but I just want to reassure you that these abstract constructs can actually be empirically approximated from the data that we use in different kinds of data-driven and numerical methods, and we have appropriate convergence guarantees as the amount of data that we have increases. So I'm going to walk you through basically these few like key axioms that we can be using for both classical and quantum descriptions of dynamics, just to highlight that they're basically the same or closely related axioms. So associated with our system, we're going to have different algebras of observables. So what is an algebra? So an algebra, just by way of terminology, is like a vector space, but it has an additional operation, which you can think of it as some type of multiplication or composition, depending on the context. In the classical level, we're thinking of algebras of observables that are functions of the state. And a natural choice in the context that we're thinking about here is that functions that are bounded with respect to our reference climatology. For those of you who are familiar with this would be like an L infinity space of observables. And this algebra is commutative under the pointwise product of functions. So classical meaning commutative. And the Koopman operator is a structure-preserving map that acts on this algebra. This is analogous to the Heisenberg picture in quantum mechanics, where basically not only it preserves the linear structure of the space, but it also preserves the multiplicative structure of the space. If you apply the Koopman operator on a product of functions, the result is the product of the Koopman operator applied to the individual factors in the product. And an algebra of this type, and again, for those who are familiar with this framework, this is what is known as a C-star algebra. A property of this algebra is they have a well-defined notion of a state space. This is not the state space of the dynamical system, it's the state space of the algebra. You can think of it as a space of statistical states. And for this choice, it actually corresponds precisely to the set of probability densities with respect to our climatology. And the Koopman operator has a dual action, or has an associated, there is an associated dual action on the state space. This is analogous to the Schrödinger picture, which is implemented by the transfer operator, how the system acts on probability density. And there is a duality relation, namely that we can either evolve observables or states, and expectation values that we compute based on the two pictures agree with one another. And we also have a framework or conditioning the state when we observe the system. This is basically Bayes' rule to obtain a sort of posterior or conditional distribution based on some event that we have measured. Think of this as being roughly analogous to quantum measurement. I will come back to it in a couple of slides. But the quantum version of these actions is basically the same list, with the difference that now we're going to replace the algebra of observables with a non-commutative algebra of operators that act on our Hilbert space. We can define that once we have a Hilbert space, is the space of bounded operators acting on it. And the Koopman operator again induces a structure-preserving transformation on that space of operators, which is now a non-commutative algebra. This is where the quantum behavior appears, and the Koopman operator acts on it by conjugation on observables. This is basically the Heisenberg picture in quantum mechanics. We again have a state space of the algebra, and now instead of classical probability densities that we had before, now we have density operators. These are trace class positive operators acting on the Hilbert space that have unit trace. So these are quantum mechanical versions of probability distributions. In the Schrödinger picture, they're involved under the dual operator to the Koopman operator. And we again have basically we can either evolve observables or states, or quantum states, and the expectation values agree. And when we can condition the state by quantum versions of events, we're called quantum effects, in a quantum version of Bayes' rule. So we have basically the analogous way of updating our state when we obtain measurements of the system. So I'd like to show this side by side, just to emphasize again that we have this common axiomatic framework for the same dynamical system. We can associate a classical, statistical, or quantum evolution. And I would like just to show now with some examples how we can use this to map different problems of relevance in climate modeling, namely data assimilation and closure in this language. Basically, we are leveraging this correspondence to translate classical problems into quantum ones. Okay, so in data simulation, we are interested in tracking the evolution of a probability density that is characterizing our knowledge of the state of the system under repeated or sequential observation. And what we want to do is to, given that we've seen already how we can assign to our system a quantum evolution, we want to create a mapping that takes us our classical probability densities. These are the states in this classical, commutative algebra of observables into quantum states. There are many ways of doing this. One way, which we in fact already heard earlier, is called, in some context, the Koopman-von Neumann approach, is to take densities and map them into quantum states that are pure quantum states, so basically rank 1 density operators, which are projection matrices that project along a vector which is the square root of the probability density. So the probability density is a vector that is integrable. It has L1 norm equal to 1. If you take its square root, it becomes a unit vector in our Hilbert space. So think of it as a quantum mechanical wave function. And we can evolve this probability vector, this quantum states, as I described earlier. The important point is that the evolution, the quantum evolution, is consistent with the classical one in the sense of recovering expectations. Now, in order to do that, we also have to, of course, to have an embedding or representation of the classical observables into quantum ones. And there is a natural choice of representing our algebra of classical observables as quantum operators, which maps observable classical functions into their corresponding multiplication operators acting on the Hilbert space. This is, for example, in quantum mechanics, the position operator is an example of a multiplication operator. One can do this for general elements of our classical observables. And so this is basically giving us a starting point now from this quantum level of description, which is infinite dimensional in general, to describe different, or to produce different kinds of finite dimensional algorithms, which are based on projections of this infinite dimensional quantum system. And this, again, can take many shapes or forms. I'm being here general, depending on, of course, the application. One can have different versions of these projections, but the point is that in finite dimensions, we're dealing with matrices of finite dimensional matrix algebras, which are describing both our observables and our states. So instead of using probability densities to describe our statistical knowledge of the system, we're going to use density matrices. And what I want to emphasize is that already with this type of description, without talking about how we encode this into actual, say, quantum computing hardware, if that is the goal, there are certain nice properties that emerge that would not be accessible classically. So one example here is that these type of projections are automatically positivity preserving. So unlike projection of functions into finite dimensional approximation spaces where you can get phenomena like Gibbs oscillations and departures from positivity, which can be important, say, if you're modeling sign-definite quantities like temperature or probability. When projecting operators, preserving positivity comes almost for free. Basically, if you take a positive definite operator and you compose it from the left and right with projections, the result is automatically a positive operator. So I would argue that there are opportunities to use properties of quantum mechanical systems, even in the context of classical algorithms. Even if you're implementing these matrix-based methods on, say, a GPU or like a classical hardware, there are certain properties that we can take advantage of. The example that I can go through quickly is data simulation, where we think of our classical dynamical system evolving under some evolution, and we are observing it sequentially and updating our state of knowledge, which is represented classically through probability densities, in a sequence of observation. So we can translate this data simulation pipeline exactly using the correspondence that I described earlier, preserving the same structure, but replacing classical objects by quantum mechanical ones, like density matrices become replaced by density operators. The analysis step in data simulation, which is the Bayesian analysis step, is replaced by the quantum version of Bayes' rule. And we can iterate this process to yield basically estimates of a forecast of observables of the system. As I mentioned, there is a data-driven formulation of the scheme. I'm happy to talk about this offline using observed data. But once we have done the training, the data simulation algorithm proceeds in direct analogy to the classical one, based on data simulation, with the difference that we replace the classical objects by the quantum ones from the correspondence I described earlier. I will show one example where we used this approach to do a simulation of the El Nino phenomenon. So basically SST fields from the Indo-Pacific. This was done in the context of a climate model, CCSM4, using this to make probabilistic predictions of the Nino 3.4 index in the model. And the output basically of this scheme at any given time, it gives you a probability distribution for different observables. This is showing here the probabilistic forecast of the Nino 3.4 index. Here, the horizontal axis is the verification time of the forecast. The lead time grows as we go down in the panels. And through this quantum state that we use to represent the state of the system, we get induced probability distributions for the Nino 3.4 index that we can use to basically predict it and characterize its uncertainty over time. The other example, this connects very much with, I think, some of the ideas that were discussed by Tim Palmer earlier in the morning, is that of closure. In fact, his paper from 2001 provided initial inspiration to work on this particular project, where our goal is to take some dynamical system that has variables which are declared resolved and some which are unresolved or subgrid scale, and communicate with the resolved variables by some fluxes. I'm denoting here by Xc. We want to replace this by some parameterized system where the evolution of the unresolved variables is basically modeled by some type of probabilistic process. And instead of using classical stochastic processes to represent our knowledge of the subgrid scale variables, we're going to represent them quantum mechanically through essentially quantum states that inform, that make estimates of the closure terms at every time step, but they evolve also dynamically under the Koopman operator, as I described earlier. So basically, the scheme is like a two-way coupling between a classical and quantum system. So this is a type of hybrid algorithms where the quantum system represents the quantum states represent our state of knowledge of the unresolved degrees of freedom, and they give us estimates of the closure terms at any given time step that we can use to evolve the state of our system, the resolved variables of our system. But the resolved variables then inform the quantum state by conditioning it using the quantum Bayes rule, and the whole process iterated to give us an approximation of the evolution of the system. So in the Lorentz 63 example from Palmer's paper, this scheme is basically able to recover the Lorentz attractor from two equations, declaring the third equation unresolved at a pretty good accuracy compared to like a basic, like a Gaussian closure. And it also is able to recover the unresolved degrees of freedom, the third dimension of the attractor, where the Gaussian scheme doesn't do that essentially by design, since it's using a coin toss, effectively like a random process, to represent the unresolved variables, whereas here we're having essentially this quantum mechanical dynamical model of the unresolved process. And it also reproduces the statistics like time autocorrelation functions of the system. So more recently, we have been working on this in the context of PDEs and cloud parameterization, convective parameterizations in cloud resolving models. So David has a poster later on. Maybe I'll leave you to ask him questions later, where effectively we are embedding different quantum states on a coarse and a classical model and applying a version of the scheme I described before for Lorentz 63 in this PDE setting, and finding that basically we can get fairly encouraging initial results, at least in some idealized simulations, two-dimensional simulation. There's still work. This is still work in progress, but yeah, the results are encouraging. So I will end, if I can take one more minute here, by mentioning a few aspects specifically related to quantum computational implementation. So what I've been talking about so far was implemented classically, but one of the main goals, I guess, of many of us here is to eventually to move towards actual quantum computational implementations, which basically means that our choice of projections in this like ladder on a Hilbert space associated with a quantum computer, and we have a tensor product structure that we want to take advantage of. I want to highlight that there are examples of systems where there's a systems with so-called pure point spectrum, where generator of the Koopman evolution, when projected to a space of qubits, is actually very efficiently factorizable in terms of as a tensor product of operators. But this is very specific to systems that have this pure point spectrum structure. These are effectively systems that are either periodic or quasi-periodic. But this is providing at least a data point where, or like an example where rigorously we can have approximations of the Koopman evolution, which are highly efficient due to the particular structure of the generator that comes from the fact that it preserves these algebras of observables. It's a multiplicative operator. The Koopman operator is multiplicative, which translates into the generator satisfied some type of Leibniz rule, like as a differential operator, which gives you this very efficient structure. So we've done this for simple examples, including the full pipeline of state preparation to measurement, and this can be done very efficiently for this type of systems in quantum circuit. But as we heard, in many talks already today, moving to more complex systems presents several challenges. But I think it's also a very interesting area to work on. So I would end with an optimistic note that yeah, let's keep working on it, and we'll see what happens.
Thanks very much for the great talk. Yeah, I think we'll hold the questions for the last half-hour discussion. So thank you again, Dimitrios. So we move to our next speaker, Meng Wang.
Hi everyone, my name is Meng. I'm from University of British Columbia. So my talk today is on variational quantum algorithms for climate and weather applications. So throughout this workshop, we have heard many great talks that addressing the theoretical gaps, that how we can use the enormous quantum power, quantum advantage to solve all different kinds of applications. Well, the works we have been working on is from a different perspective, is that when you're having those proposals, you have some theoretical advantage you have that you think that through those proposals you can achieve. But when you're actually running those quantum algorithms on the actual devices, there are another hidden layer of challenges that can greatly compromise your expected improvements from your design. So the kind of works I'm presenting today is specifically addressing those challenges. So the algorithms we're focusing on is called the quantum approximate optimization algorithm, is the QAOA. This is a very representative variational quantum algorithm. The main applications of this algorithm includes first the social network analysis, VLSI designs in the classical architecture design, and supply chain management. The common feature of those kind of applications is that they all can be represented as some form of graphs. So fundamentally, those are kind of the graph problems that you can reduce those problems into a graph and then solve. So for the climate and weather application, the things that we can use this to solve is the sensor placement, for example, infrastructure protection, evacuation routing, resource scheduling, and mesh partitioning. So those are also some of the applications that you can reduce to a graph, so and then used by the QAOA. So those are the applications we can address with this algorithm. So for the general variational quantum algorithms, including the QAOA, the general execution flow is that we have this what we call the parameterized quantum circuit. The difference is that this kind of circuit contains some tunable parameters that we can change. So we're given some quantum algorithm, quantum circuit, but within this, some of the gates, we can change how the rotation angles are, like for example. And what we do is that we send this to execute on the quantum device. Those devices are usually held on the cloud. And we get a result from this. We calculate some expectation value, and those expectation value is feedback into updating those parameters. And the two works I'm presenting today, one of them is addressing this parameter updating part. The other is addressing this cloud execution of those VQA jobs. So the first work is called the REQAOA. It's efficient variational optimization through circuit reduction. So I mentioned that the QAOA is addressing those problems that I can represent as graphs. So the QAOA circuit, how do you construct such circuits? So first of all, we have a circuit that has the same number of qubits as the number of nodes in your graph. So here we have a 4-node graph, and correspondingly we have a 4-qubit circuit. Then for each of the edges, so here we have an edge between node 0 and 1. So we have one parameterized RZZ gate between first 2 qubits. And the RZZ rotation angle, again, as I mentioned, it can be changed. So we add one gate for each edge, and then also one last layer of single qubit rotation gates. And those single qubit rotation gates are also, their rotation angle can also be configured. And for the QAOA specifically, this part is called one layer. So this part, each layer is going to have 2 parameters. We have arbitrary number of layers. More layer you have, more better result you're gonna get. But more layers meaning you have more number of parameters, and also your circuit depth is deeper. So there are other trade-offs. So when we're doing the classical optimization, we're usually here I'm plotting the so-called optimization landscape. So we have 2 parameters, and their corresponding expectation value is plotted by different colors. We usually start from some initial points. Those points are usually randomly initialized on this landscape. The 2 optimal points, so there are 2 optimal points on this landscape. That's our target. And we do the classical optimization, and we basically traverse through the landscapes to converge to one of the optimal points. So the goal in this point is that we want to identify the optimal parameters. But the challenge is that we have those devices are noisy. And on the left is the ideal landscape, which is clearly easier, pretty easy to converge to the optimal point. But your noisy landscape might look like this. We actually run the same QAOA circuit on the IBM devices, and this is the result we're getting. It's totally distorted. So you're not really getting a meaningful result from this on the noisy landscape. Our insight was that when you are having a smaller circuit, meaning you have less number of qubits and less number of gates, you're going to have fewer errors because those errors are corresponding to each of the gates you are executing. And also the QAOA optimization landscape is not unique to individual graphs. What I mean by this is that, for example, here we have 2 landscapes. One is from the 10-node cycle graph, the other is from the 7, and their energy value, the expectation value is normalized to 0 and 1. After normalization, we see that they are almost identical, and they share the same optimal points. And remember that I mentioned that during the first part of this classical optimization, the goal is not trying to identify what's the exact expectation value is, where the goal is trying to identify the parameters of those optimal ones. So we can optimize QA parameters with a reduced graph. But how do we find such graphs? Well, look back at the circuit constructions. We see that most of the QA operators are actually originated from those edges. And then we also know that those edges within a graph affects the node degree, which means for each node, how many edges are connected to it. So we use the node degrees as a heuristic to find the reduced graph. So the general, I won't go into too much details, but the general idea is that we're gonna start with some initial random nodes from this, when constructing this reduced graph, and then choose a random neighboring node from this one. We have two candidates, node 1 and 2. And then we just, in cases, we just choose random one, and we create the neighboring graph from this. And we decide, is this a better neighboring graph than without this newly chosen neighboring node? If it's yes, then we just accept this and continue. But if it's no, then we're not directly rejecting it. We're doing this with a so-called simulated annealing process, which avoids we converge into some local optimals. So we have some discussions on why this kind of form really works, that you can end up with a reduced graph that has a almost equivalent optimization landscape. And then we repeat those steps until we find a graph that is close enough to our original graph in terms of the optimization landscape, and also small enough that we can, that is more tolerant to noise. So the overall design is that we start with some input graph, say SG, and we do this graph reduction and get the reduced G prime. We do the parameter search with a G prime. And once we identify those optimal parameters, we use that with the original input graph G, and then finally get the actual solution. And this highlighted part is RegQA. So the results we're getting, we have evaluated our design through 3 graph data sets. And the landscape here, we're measuring at the mean square difference between the original graph and the reduced graph. So we can see that the mean square difference is less than 0.02, which is almost negligible if you look at the actual landscape shape. And the reduction size we're achieving is that we're reporting two. One is no reduction, the other is the edge reduction. The no reduction corresponding to how many qubits you are saving. The no edge reduction corresponding to how many gates you are saving. So we're achieving about 30 to 40% across the two. And this is the key result we're getting. Again, we're running this on the actual quantum device. On the left is the ideal landscape running in the noise-free circuit simulations. In the middle is the baseline. You run the original circuit directly on those devices. And on the right, we can see that although we're still affected by the noise, but we almost recover where the optimal point location is. Yeah, so that's the first part. The second challenge I want to talk about is this circuit execution. So when we're having those variational quantum algorithms, I mentioned that we want to schedule them on the quantum devices that is running on the cloud and get the result to update. But in practice, we have more than one quantum devices that we can choose to run our job. And for each of them, they're going to have some queues for the jobs that you want to execute. So there's this natural selection. Oh, which device do I want to run my job on? One of the key factors is that those devices are going to have different error rates. So now we have different qubit technologies, including superconducting, trapped ion, neutral atoms. The key differences between them is they all have different error rates. Right now, the trapped ion devices have a significantly lower error rates than the others. So when we're choosing the devices, the choice becomes, oh, we have those devices with different error rates, and we can characterize them with different fidelities. The natural selection would be, oh, let's just use the high fidelity device because that gives us the best result. Well, that's also the same for all the rest of the users. So the queue for that is quickly pile up. Well, once the queue is just too long, then some of the users determine, oh, I want to opt for the second best device. Again, the queue can pile up quickly, and some of the users really want to get their results to see what it looks like. And that's the result. They're just choosing the lowest fidelity device. And the trade-off here is that we can measure in latency and fidelity of your job. So for the best device, it gives you the best fidelity, but also the longest latency. And so on for the mid fidelity and lowest fidelity devices, where you basically trade fidelity with latency. Our goal is we're trying to have the lowest latency while with the highest fidelity. So for the variational quantum algorithms, it's actually make this scenario worse, because for each variational quantum algorithm job, we need to run multiple circuit executions, and this repeated loop can make this entire queue situation much worse. So we're using this sphere shift to represent one circuit execution, and we usually gonna do tens of restarts for each of the end-to-end optimization iteration. Overall, this creates a huge circuit execution overhead. And I should mention that there's this runtime hybrid device access service that is provided by those cloud service providers like the IBM. The idea is that once you have queued up for a certain device, then for the consecutive following jobs, you can just jump into the front of the queue without joining the queue again. But this doesn't solve the system-wise queuing problem. So the key insight from this Concord work was that not every iteration requires the maximum fidelity, and not every restart needs to be carried through the completion. So we see that, again, do this optimization trajectory. If we categorize the entire optimization path, we can categorize that into exploration and fine-tune stages. And we see that generally, if here we're running on a so this noisy landscape is also from simulation. If we're just running the same optimizations, the fine-tune part can diverge, but in the initial exploration part, they're all actually heading towards the same directions. So the exploration is more tolerant to noise, makes us to be able to run those on the lower fidelity devices. And also, not every restart needs to be carried to the completion. This is because usually we start from some random points, and they all lead to different finish points. And some of them are trapped in some local optimals. The only thing that matters for us is those globally optimal solution. And we can categorize those globally optimized points early in the stage. Here I'm plotting that the x-axis shows the post-exploration phase, and y-axis shows the final result. We can see that the ones that are finished better after exploration tend to finish better in the final fine-tuned exploration phase. So the general idea is that so we partition the VQA tasks into exploration and fine-tune, and we do the exploration on the lowest fidelity device, and then only carry on to the highest fidelity device with the best performing restarts. So overall, the result is that we're doing this queue simulation, and we compare with several scheduling policies. First of all, is the least busy scheduling policy. This gives us the best throughput, but the lowest fidelity. The low weighted will tend to put more weights for the devices that has less number of queued jobs. It's very similar to the least busy result. For the fidelity weighted, it's trading the fidelity, putting more weights on better fidelity devices, but still gonna opt in for the lower fidelity device if it's just the queue is too long. The best fidelity is always aiming for the best device, but again, the throughput is pretty bad. The EQC work was one of the prior works that's of the state of the art. It's trading the throughput with execution fidelity. So overall, our work provides a fidelity and throughput trade-off. So this is the result showing that when on the same device where you seemingly have the same error rates, then you can still have this error difference if you're running those error mitigation methods. So overall, as a summary, I want to highlight that quantum computing can also be seen as a system problem. There's this hidden level layer of challenges. And our work at QA proposed to use smaller workloads, which give you a higher noise tolerance. The Concord work is doing a adaptive multi-device scheduling, and overall they reduce errors, latency, and cost. And the goal of those work are doing a full stack quantum optimization. And with that, it concludes my talk. Thank you everyone for listening.
So our last talk for this session is Priyank Dubey from Texas A&M University.
Howdy. My name is Priyank Dubey. I'm a PhD student at Systems Engineering, Autonomy and Knowledge Lab at Texas A&M University. So in order to get better weather and climate data, we just don't need more satellite. We need them to be working together perfectly so that they can coordinate with each other. And in this talk, I'm actually going to talk about such engineering bottlenecks in order to design such constellations and how can we use quantum computing for it. So weather and climate applications already relies heavily on the satellite data. So as you can like see in NASA's A-Train, which is a constellation of around 3 to 6 satellites, which flies multiple heterogeneous instruments to get the better quality of data from the aerosols and clouds, which no single satellite can provide if like it's equipped with one single sensor. And similarly, like for the cost, there's like a constellation of small set, which is cosmic 2, and that alone contributes to around 4,000 to 5,000 daily atmospheric profile for global numerical weather prediction model. And the polar orbiting satellites like NOAA's GOES can provide like near real-time coverage for time-critical phenomena over like certain area. So in order to like connect all these threads, we kind of see that satellite constellation already contribute a lot towards the weather and climate data applications. And now like in this talk, I'm gonna talk about like how can we design those smart constellations. So before we move further to the constellations, we actually like have to define a coverage metric because it's a fundamental figure of merit which directly translates between the trade-off between like the science gain versus cost, because like as a systems engineer you have to see this trade-off carefully. And the coverage can be further like classified into two broad categories, which is like geographical coverage, which is like coverage on the ground, and the temporal coverage, which is the time distance between the consecutive observation of the same target. And which like temporal coverage can be like called as revisit time also in like broad way. And this revisit time is very critical for like data assimilation because it directly translates to the continuity record of that particular area which we are focusing on. So why can't we just like throw this optimization problem to a classical solver and call it a day? So there's like a couple of problems with this particular scenario because revisit time naturally translates to mixed integer program, which we have seen in the like previous slide, which roughly like translate to set covering problem, which is NP hard in nature, meaning like if you go on increasing the targets, time steps, and number of orbital slots, like which is the design space where we can put the satellite, it combinatorial explodes. And on top of this, like there's another challenge with MIL formulation, basically because our objective, which is ART and MRT. So ART is the average revisit time between like consecutive observation of your all targets, and MRT is a maximum revisit time, which is like a max gap between two continuous observation seen through all targets over all the times. So in order to accommodate this like non-linear form into the MIL formulation, we generally use some linearization technique like Big M, which further like introduce more inequalities and in turn introduce more auxiliary variables, inflating the problem size. And exact solver actually can solve this for small and very arranged instances. But as we move towards the realistic scenario where we bring like multiple orbits and multiple sensors, then this get tricky to solve in like practical time limit. And so that's the area which we are planning to tackle with this like workflow. So why quantum at all? Because quantum theory, we in principle promises us to solve like large scale, promises us to search a large scale solution space simultaneously exploiting the phenomena from quantum physics. But there's a like we are still in the NISQ era where we have limited connectivity. First, we have limited number of qubits, which can represent our design space. Then we have limited connectivity. And top of that, we have like error, which really like explodes as we go on increasing the number of gates and number of depth. So like how this actually works, like we have seen from Meng's and Brandon's presentation, that it actually works like kind of on variational principle, where like we encode our problem into the Hamiltonian energy, Hamiltonian, then we use different algorithms like variation quantum eigensolver and QAOA to find the lowest energy state which correspond to the optimal solution. So if you like look at it from the outside, there are like two engineering problem which you can see. First, like how do you effectively map your problem of interest to the Hamiltonian, which can be directly implementable on current hardware. And second, how do you ensure that your map problem actually like respects the boundary of current next devices. So second point is very critical here, because like most of the work are currently focused on first point. So before I go deep into math, I just want to make an analogy here that instead of visualizing the slot as slot, what if we look at it as a charged particle, and what will be its charge? Its charge is like how well it can observe your targets at a given point. So now there's a key insight here. So if like two slots observe the same target at the same time, they are like kind of redundant. So that's wasted coverage. Therefore, we want to penalize that assignment if like our solver try to make. But in order to penalize that assignment, we can actually like introduce a repulsion like interaction between the slots. So here on the like in the middle panel, you can see that instead of looking from the slot or like coverage problem, we are now looking at a interaction problem on the time scale, like linear time scale. So with this like analogy, we can also like conclude that if two slots are observing the same target at a distant like temporal gap, then there shouldn't be any repulsion, or there should be like close to zero repulsion. So this gives us some idea that how we can like translate first point, like how we can translate our problem of interest into like the problem which can be implemented on hardware. I'll go into the math later, but our problem becomes like instead of just minimizing the revisit time, if we can minimize the placement of charge on this temporal interaction field, like that ring particularly, which is like the equilibrium state of all the slots. So this is actually the mathematics which maps this problem. So from the last slide, we kind of saw that we want the interaction to be just between the slots when they are like very close to each other on a temporal scale. But if they are far apart, we don't want them to interact at all. That's something like screened electrostatic potential rather than a classical Coulombic potential. And actually we experimented with the classical like Coulombic potential, where like we have infinite range decay. This was hurting our like objective. So with that in mind, we went on with like Yukawa repulsion kernel, where we have tau which can be specified as the maximum tolerable gap where like we want the interaction to be, and we have a delta t cyclic because like our timeline wraps around the simulation horizon, which also translates to repeating ground track of satellite. And like once we have that kernel, if we aggregate it over all the time pair over all the target, we will have a single repulsion matrix which represents the interaction between all the slots with all other slot, which will be like one of the term in our energy Hamiltonian. So in the energy Hamiltonian, like at the very bottom, you can see like the first term represents the penalty, which is like very well covered by Brandon. And second term is like we want to maximize the coverage. And the third term, which we just saw like the interaction between the different slot, wasting the coverage assignment. So this is not like just a heuristical mapping. We actually have a mathematical bound, like how this is equivalent to minimizing the average, minimizing the revisit time problem. So particularly we focused on average revisit time now, but there can be a similar analogy for maximum revisit time as well. So the good news is that we have a Hamiltonian which is like quantum ready. We can directly like implement on the hardware. But the bad news here is that the interaction matrix which we just formed like couples all slot to all other slot, not just the neighboring slot. But we saw like in the NISC hardware, they have limited connectivity. Not all the slots are covered. Not all the slots are connected to all other slots. So in order to bridge that gap, like how it works realistically, if you implement a problem on a hardware, they insert the swap operation, which moves the quantum information around the entire chip, which increases the number of gates, which further increases the number of depth of the circuit, and which in turn gives us the noise level, so much noise, which we talked yesterday. So here, for representation, you can see we have coupling graph on the right. So gray lines represent what is required from the RIJ, and bold kind of represents the available physical connectivity, which is on the hardware devices. So how do we tackle this? Again, we went back to physics and borrow a phenomena which is called renormalization group. It's a very powerful mathematical framework which lets us observe a system from different scale of space, time, or even energy. So how it works actually, so we see that complex systems may have so many microscopic degrees of freedom, but for some particular objectives, we just want large scale behavior. So instead of looking at a system at very deep level, we can zoom out the system and look at the coarse level. So on the left, you are seeing that very traditional 2D Ising model formulated by Onsager for classical, for predicting the phase transition. So that was where the renormalization group was born, where we can group the spins based on their interaction and also other factors, and we can form that clusters. And then instead of looking at entire system, we can look at this coarse-grained network, which will give us the idea about how the system behave. And similarly, in the social media network, we have individuals which are interacting based on different traits, but based on interaction between the individuals, we can formulate the community. So in graph theory, this community formulation is a very big problem, and there are so many algorithms. So with this in mind, we apply that same RG-inspired approach on our slot network. And as you can see on the very right, that as we go from the entire network to the coarse-grained network, we go from micro degree of freedom to macro, and our resolution decreases as we zoom out. And this actually gives rise to very interesting phenomena, in terms of if you track their von Neumann entropy and specific heat capacity, which I'll be covering in the poster afternoon. So feel free to drop by. But how do we first start? For our system, we just form a co-observability network. We track the coverage utility over all targets and over all time step, and pair the slots together based on their co-observability. And then we use a standard Laplacian renormalization group approach, where we calculate the Laplacian of the graph, and we get their k smallest eigenvalues. So which gives us a low dimensional embedding, where the slots which are structurally similar and redundant for observations sits very close together, while the structurally distinct slots very far apart. So how this work? Because there's one intuition that the Laplacian can actually gives the Fourier basis for the graph, and the lowest eigenvalues represent low frequency, which represent the long wavelength. So you can interpret it that behavior with lowest eigenvalues travel far apart. So these are long range behavior, which exactly we want. While the more large eigenvalues, they represent very short range behavior, noise on a very slot level. So we don't want to integrate that in our network. And once we project that complete graph into the low dimensional embedding from the k smallest eigenvalues, we get these nice, beautiful clusters. And then within the cluster, we actually pick representative node. And then we feed this reduced manifold into the QO machine, or a real quantum computer. And this K can be actually like tuned based on the hardware which we are dealing with, and also based on like the classical eigengap heuristic, like where we assume where we see that sudden gap in the communities formation, or like the entropy and specific heat capacity. So this is pretty much covered well, and I will skip that. And once I want to give you the overview that we have orbital slots, and then we have this Hamiltonian formulation and coarse graining using renormalization group on CPU, which is exactly like something can be implemented using quantum computer. And I'm going to present this in IEEE Quantum Week in the coming September. So this is our like overview of the workflow. Now, like we do it on a case study where we consider like some realistic target over the US, and then we consider sun synchronous orbit, which actually like have an orbital plane presses around the Earth at the same rate like how Earth orbits the sun. So this provides us a consistent illumination, which makes the observation like in the same time. And we like did this for like 10 minutes time horizon, 24 hours window, and propagated the orbit with elevation degree of freedom like 5-degree threshold for visibility. And then like we have like experimental proof with 48 candidate slot, which is exactly solvable using MILP. So we verify that our like method is exactly recovering the optimal solution which was given by MILP on a smaller scale. And then as we go on increasing the number of candidates, we observe that within the reasonable time limit, like if you run MILF for like 3 hours, it will not guarantee the optimality. It will predict the theoretical gap of 60%, but at the same time, if you give the problem to our method, it will give you the better minimum average revisit time for that system. And similarly for this, like as we scale more, we observe like same behavior, but here we are like simulating it with ideal scenario with no noise and 15K sorts. Then we went on a hardware without any error mitigation, and we observed that like performance fell through. Then we apply some error mitigation method, and we see they're like still recovering the optimal solution, but you can't expect it to be the ideal scenario. With this, I will conclude. Thank you.
Yeah, so if there are questions in the room to any of the speakers or online, in the room, walk up to the mic. And online, please feel free to raise your hands. Be the first question, Ruben.
Yeah, thank you all for your excellent talks. So there was a little bit of discussion on warm starting for the QAOA. I don't know much about that algorithm, but I'm curious if you all could speak to that a little bit. How do you find the warm start? And also, I've done a little bit for PDE, well, really linear systems. You also have to carry the variational parameters through to maybe, I guess, it's non-trivial how to figure out how to transfer your variational parameters, at least in the application I was looking at. But could you talk a little bit how the warm starting method works in optimization algorithms?
Yeah, I guess I can start. So I think that there are first of all two kinds of warm starts. First, you can warm start the variational parameters. Also for the QAOA, you can also set the initial qubit state based on the bit strings that you think that can provide you a better result or closer to the solution. So for the first kind, the warm start of the variational parameters, that's actually the central idea behind the RegQA work that we did. We found that, we can transfer the optimal parameters between different data sets. And the thing that we figured out, given two graphs or two problems, how do we figure that if they can share the same optimal parameters? We found that, we can get this information from the node degrees. That's why we use that metric to do that. And I think there are works that studies, there are class of graphs specifically for the QAOA. I don't know about the other VKA algorithms, but for the QAOA, when you're looking at the graphs, there are certain types of graphs that have this transferability. And even the average optimal parameters. So if you're thinking of you having a large set of graphs, they all have different structures. But if you just take the average or the mean of those variational parameters, they all perform pretty well for any given random graphs. So there's this transferability that enables the works like QA. And just a quick comment on the second type of form server, which I believe people have figured that if you set the qubit states to an initial state that is seemingly closer to the solution space, then it actually performs worse. So your final solution is now better.
Okay, I guess a follow-up question on the first part. So is the physical intuition that you're solving a simpler graph and you're using that sort of to help you figure out like an approximate solution for the more complex graph that you're actually interested in? Or I'm trying to borrow ideas from the methods that I've used, or does it not relate to that at all?
So we can get some, but the physical insights are saying that from the QA constructions or the fundamental Hamiltonian part. So we we did empirical analysis, and based on that, we figured some of the features, including the node degree, that can help as a feature. But I think we had some in our paper, we had some discussions onto why this makes sense. And we rooted that back. We don't have a full theoretical proof, but we think there are some connections to how the QA operators work.
Okay, thank you.
Hi, I have a few questions. So the first question is, so I believe for both of the applications are Kubo, right? Not Hubo, you talked to me yesterday. So I might miss that. But if it is a Kubo, QBO, why don't you using, like the D wave instead of you formulate as a QA OA problem? On D wave, you will have more physical qubits to use. So this is my first question.
Yeah, as a matter of fact, like we have used like D-wave quantum annealer with like Dr. Guillaume here from JPL. So for the earlier problem, but this was like instead of just looking at just Cubo architecture, I want to expand this to like a circuit level problem rather than just like be constrained in the like Cubo rising model system. So I will probably want to like extend it to a method where we can actually like map the exact problem with higher order like interaction, which like Hugo we talked about yesterday. So that was the scenario.
But for the presentation you just did, it's a Kubo problem, not Hubo, right?
Yeah, it's just a Kubo problem because like, so when I talked about the mathematical equivalency between the Yukawa repulsion kernel and the objective, which is like minimizing revisit time, there's a like in the mathematics we made an assumption that no three orbital slots can have like interaction. So that's the assumption which like led us to formulate the problem with like second order interaction like binary. So that's why like it's just a Cubo right now.
I see. And my second question is related to a benchmark to solve the MILP using the classical solvers. I'm not sure which particular solver you are using, but there are a lot of different methods. From my experiences, for example, if you're using the Bender's decomposition, that's solving the ILP as the master problem, and then solving the rest part of the problem as the sub-problem, it's pretty fast. I'm actually surprised to see the computation time on solving the MILP is that long.
Yeah, like so I'm familiar with this Bender's decomposition, but like for this particular scenario, like we have been using Big M method. Like so if you like, I cited one paper from William Rogers in JSR. Like so he formulated this as a Big M method. So we just like took the approach which is like used standard in the field and compared with R. And just like I didn't have time to mention this here, like we are not talking about any quantum advantage. I'm just talking about the utility that there's a possibility that we can integrate quantum as a part of routine in solving that type of problem, and we can get the solution sometime better or sometime equivalent in the given amount of time, which is like realistic on our machine. So
okay, thanks. And okay, I have another question actually to both of you who are using the QOA. So both of you using the graph theory and application on that, but I didn't quite follow what exactly like for your application, try to solve the QAOA on the subgraph, and I maybe missed that. How will the optimal solution on the subgraph will be kind of representative of the solution to the big graph?
Yeah, so this is related to the transferability of the QA parameters that is brought up by the first question. So there are studies that showing that between different between different QA problems, there's this transferability. And well, I guess the underlying theoretical foundation of why this transferability exists, which classes of graphs that can have this transferability, I think that is not fully understood. But what we did is we did empirical analysis and found the type of graphs that we can use as the reduced version to identify this optimal parameter.
Is it any particular requirement on the type of subgraph? Like, can imagine that it can be transferable across all types of a graph.
Yeah, for sure. It's only a constraint. We actually tested. So in our evaluation for any given graph, you can have hundreds or even thousands of subgraphs. We evaluate all the candidates and only figure that a very small fraction of those subgraphs can provide this kind of transferability. And the metrics we're using, the null degrees, those kind of metrics, does lead us to those very small fraction of transferable subgraphs.
Yeah, I just like to jump in here because like his approach is actually looking at a graph without like domain kind of scenario. But in my approach, I'm like more focused on the problem because like if you have particular knowledge about the problem itself, you can actually like form the clusters which will couple together the solution space which are like redundant, which might be redundant to choose from, and then from those like clusters you just pick representative slots or like representative decision choices, and then you can run the loop. I mean, like depending on how capable your hardware is, you can like try to choose like top 3 or top 4 from each clusters and then try to run the problem. So that is like my approach, but his approach is like in general more like generalistic without problem dependent.
Thank you.
Thank you all for the very interesting set of talks. I had a question for Dimitris. So if I understand your approach correctly, you use the Lorentz 63 system and then you applied Koopman operations on it. And then that allowed a linear representation of the system. And did you have to do anything special to handle nonlinearity in the system, or it's implicit in the method?
So it depends on which version of you're talking about the closure problem?
No, not the one before where you showed the state space.
Oh, this was just an illustration, but in general, when you are speaking about the evolution of observables or probability distributions under the system, this evolution is intrinsically linear. It's basically a linearity of the Koopman operator or the Perron-Frobenius operator. And if you're thinking about observables or distributions which are defined in these Hilbert spaces that come from this invariant probability distribution, because you have to choose the Hilbert space, the Koopman operator is unitary. So then you can pick your favorite method for approximating unitary operators, and that handles like the nonlinearity sort of like under the hood.
Okay, and I think I missed it. How many qubits did you use to simulate the system?
This was all the experiments until the very last figures I showed were done, classically. So this is where you would call quantum-inspired implementations. Typically, I would say the dimension of the Hilbert space used in the numerical experiments was of the order of a few hundred, 500 to, let's say, 1,000. So in terms of qubits, I will not haphazard, I guess, but the Hilbert space dimension was of order 500 to 1,000.
Yeah, just trying to connect it with Tim Palmer's talk this morning. He said something like 655 or some qubits, right? Degrees of freedom, at least, for the system.
I'm not sure, but we may be talking about different approaches here, like that also targeting different representations of the systems in different Hilbert spaces. Yeah, we'll probably have to sit down and...
A quick question for the folks who were working mostly on QAOA and variation algorithms. So do you have any thoughts on how you plan to tackle the barren plateau issue as these problems scale? Have you looked at specific problems and their scaling for different sizes, and how maybe some of your techniques can mitigate the eventual problem with vanishing gradients at scale?
Well, I guess generally speaking, the barren plateau is a huge challenge for those variational algorithms. I do see there are approaches like choosing different kind of mixture operators, like for QA. But generally speaking, I think it's pretty challenging, and we do need better mitigations to make this classical optimization loop much more effective.
Yeah, for me, like it will really depend on the problem. So how well are scales separated in a problem? So because for my method, we are like just gonna form clusters based on the scales. So if your problem has like a good scale separation, then it shouldn't be any issue if you scale to a large number, because at the end you are gonna take like top 3 from each cluster. So I don't know if that answers your question.
Yeah, so the current issue and state of the art that I've noticed at the moment is that so for depending on the Hamiltonian that you're trying to simulate using VQE, there's a split between a Hamiltonian being classically simulatable, and for those who are not classically simulatable, those tend to have really hard barren plateaus. So there's this kind of gap of identifying like the correct Hamiltonian where a VQE algorithm or a QAOA algorithm would work in that particular case. But I don't know if you folks, for the techniques you've looked at, if you've looked at the specific Hamiltonians and if there's a property of the Hamiltonian that would somewhat bypass the barren plateau problem.
Yeah, actually, so for us, we're more focusing on the execution overhead part of those variational algorithms. We had some experience running those and running into this kind of barren plateau problems, but not really trying to address in those yet.
Yeah, like for me as well, because like this was very domain specific, so I didn't go a lot into the other side because that opens the other door. Like as you were talking about, as soon as you couple the quantum with the classical, that is like very separate issue. So I was like trying to play in the other.
Great. Yeah, I think we'll end this session. Thank you again for great talks.
All right, welcome back, everyone. Okay, we're going to get started with the virtual poster presentations. The virtual poster presentations will be max 5 minutes of presentations, and then we'll have time for 1, 2, 3 questions per person. Now we're going to get started. So please take it away, Hedwig Keller from the German Aerospace Center.
Yeah, thank you for the introduction. So as mentioned, I'm Hedwig Keller from the German Aerospace Center. You already heard a bit from my colleagues yesterday and earlier. So Dirk Schwabe and Nils Klement and our work on how to integrate quantum computing and Earth system models. And I will focus on the quantum machine learning based parameterizations for Earth system models. Next slide, please. Okay. Since not all processes can be resolved at the resolution that we run our model at, so for example, microphysical processes, we use parameterizations to describe these subgrid scale processes. But they are often not very accurate and could be improved by machine learning, or in our case, quantum machine learning based models that we train on high resolution data. So we run over a short time high-resolution simulation as training data, coarse-grained it to the preferred resolution and calculate from the target variables. And then we train on this data our hybrid ML-QML models, and finally couple it to the QML-based parameterization to our Earth system model. And so far in our group, with our industry partners, we have developed several QML-based parameterizations. So, for example, Cloud Cover and Cloud Microphysics. The last one was developed by our industry partners. And then the one that I'm going to focus in later is the atmospheric boundary layer height and the atmospheric boundary layer turbulence. Something that you should notice that they were all trained with state vector simulation on a simulator, and the Cloud Cover was also trained with shot noise, but for the noise, for the most part, this was trained in an idealized noiseless setting. So the atmospheric boundary layer is the lowest part of the atmosphere that is directly influenced by the surface of the Earth. And it's important to model for the exchange of heat, moisture, chemicals, and momentum between the atmosphere and the surface. At a height of the atmospheric boundary layer, this should be self-explanatory. It's the vertical extent of this boundary layer. And the turbulence for this parameterization describes the turbulent vertical heat flux. So first, for the parameterization for the boundary layer turbulence. So my colleague developed several variational quantum circuits with tradable frequency spectrums, testing local and global observables, and then tested it against classical neural network as a classical baseline. And you can see here there are two scores in color, the QNNs with different number of qubits, and in gray the classical neural networks. And the QNNs in the classical neural networks achieved a similar performance and generalization skills. But something that that was observed that we've also already seen for the cloud cover parameterization is that the QNNs have or on average, a more stable feature importance than the neural networks. Then for the boundary layer height, so this has 76 input features, and to make it more manageable, it was compressed to 8 input features using interpretable or physics-aware interpretable feature engineering. And then also different ansatz for QNNs was compared here to a classical multi-layer perceptron. The MLP had a slightly better root mean squared error, R2 square, and mean average error, while the QNN had was more stable in the sense that it had a lower seed-to-seed variability and had a bias closer to 0. So these were the different parameterizations. The evaluations so far were only done offline. So the next step would be to couple them to the Earth system model. But since quantum hardware, especially with HPC support, is so limited, we need to use either a simulator, which is computationally expensive and will slow down the simulation considerably, or we can use a shadow model or a classical surrogate. So a shadow model, this was defined in a paper by Jabi et al. And this is just a classical model that is trained on a quantum circuit. To use the internet, several different methods that you can use, like quantum Fourier model or tensor networks, or if you have a
warm applause for Hedwig Keller. Hedwig, I see you're coming back. You cut out, so we move on to the next speaker, and we'll circle back to you at the end. Our second speaker is Giulio Malinverno from the University of Zaragoza and the Italian Factory for Compressed Air Machines. Giulio, please take it away.
Hello, good evening or good afternoon. I'm Giulio Malinverno, PhD candidate at the University of Zaragoza and also employed at FIMAC SPA, that is a small company in Italy. My talk afternoon assess a proof of concept for a quantum computing approach applied to design of refrigerant ejector devices, also called the jet pump, and used in several industrial applications. In case of environmental control system, ejectors are employed as mixing valve, mixing high temperature, high pressure motive stream, typically bleed air coming from engine, with a low pressure, low temperature driven steam, exploiting the Bernoulli and Venturi effect. Governing physics, as seen in the slide, is just a conservation of mass, momentum, and energy, with the application of some empirical coefficient found, for example, in standard like the SEA AIR 1168. However, in a real application with duct downstream back pressure, feedback, the total mass flow, and also there is to consider the effect of compressibility with appropriate correction coefficient. That's for classical quadratic equation in a nonlinear system that can be solved, for example, with a numerical iterative method here displayed, but it can be subject to numerical instabilities, or classically, the design of the jet pump can be solved with the use of full CFD simulations, which are indeed very accurate, but at the same time very expensive in terms of industrial time. Next slide, please. So to overcome this issue, the proposed approach consists in encoding the unknown, namely the Riemann ratio, the pressure rise, and the compressibility factor in a single binary vector, and applying the minimization with quantum annealing of the least square residual of the discretized set of equations, having rewritten them in a quadratic form with the Kubo formulation. However, due to the nonlinear equation, the residual contains cubic and quartic terms, so to be precise, the results obtained is technical high order unconstrained binary optimization, or UBO. To solve it with the Kubo formulation, the quartic and cubic term have been reduced to quadratic and linear terms with the introduction of auxiliary qubits. At the end, the classical Kubo formulation can be found and used to solve it with the quantum annealing. This methodology has been validated with a reduced model reproducing a real ejector design. And as a reference, traditional computational fluid dynamics simulation have been performed for the same operating condition. As seen, the validation involved both analytical and quantum algorithm, and both solutions follow the CFD results with an accuracy of more or less 2-3%, but with a significant shortened execution time compared to the CFD simulation. Basically, the approach has been validated and confirmed that the quantum annealing can be used also for industrial application and give comparable physical and interpretable sizing tool compared with the CFD simulation. Thanks.
Fantastic. Thank you so much, Giulio. I have one question. Giulio, you said you validated your quantum annealing results with analytical formulation. Did you see any advantage in using quantum annealing? And this does not need to be a quantum advantage. It can also be a practical advantage.
Well, to be fair, the validation has been done not on a real quantum computer, but on a simulated environment. So let's say the results, how to say, are not, we have not tested a real quantum hardware. So the results, of course, when it's positive, have to be validated after with the real hardware. From a technical, let's say, point of view, from a application, I am speaking as a design engineer, I can say that the formulation can be easily applied to an industrial case. And compared to other approach, what I appreciated is the physical meaning of the method. From an engineering point of view, this is important because I can follow the process and give a physical meaning at each step, so a better control of the process.
Fantastic. Excellent. Thank you so much, Giulio. And then we will have our third virtual poster presentation presented by Xiang-Yu Li from the Pacific Northwest National Laboratory.
Hello, everyone. Thank you for the intro. So today I'm going to introduce you about the potential quantum advantage for the nonlinear multiscale complex system. Because our climate system is no doubt is really like a multiscale complex system with a lot of nonlinear problems. Like here we show the particle turbulence interactions, and even in terms of general circulations, is like a nonlinear multiscale system. So in the last few years, we have a lot of quantum algorithms that come out to deal with this like a strongly nonlinear system. So the pioneer work by Andrew Childs and Xing and other co-authors really provided one of the foundational work of this. But from that work, we understand that because of this linear nature of a Schrödinger equation that other colleagues also discussed a lot in the past 1.5 days, the ability for the quantum algorithm to deal with multiscale nonlinear complex systems is very limited. So here we provide a new framework for this. Instead of forcing linearizing the Navier-Stokes equation directly, we could just step back and look at the physical description of the fluid dynamics, because the Navier-Stokes equation is just one of the mathematical model to describe this in the microscopic framework. And we have this macroscopic description of fluid dynamics. And there we also have the mesoscopic, that is basically describe the fluid dynamics, Boltzmann formalism. So there, when we reformulate the Navier-Stokes, the fluid dynamics in the Boltzmann framework, we could localize the strong nonlinearity to transform the Reynolds number governed nonlinearity into the local Mach number governed weak nonlinearity. And then we apply these linearization methods that are mostly only useful in the extremely weak nonlinear regime. And therefore, we can basically show a quantum query complexity that is scales with logarithmically with the number of degrees of freedom for any arbitrary Reynolds number. So this really opens the door for simulating realistic systems in a quantum algorithm framework. And a further application of this is that if you consider the reaction diffusion processes in the biophysical systems where you have to solve the Schrödinger equation to calculate the reaction rate. So this is also related to our atmospheric chemistry where we also need to estimate the reaction rate. At the same time, we also need to deal with these nonlinear processes of the reaction diffusion case. So using the quantum computer, we are able to, again, in the algorithmic framework, to calculate the reaction rate online and together with solving the nonlinear reaction diffusion equations and get a exponential speed up for reaction rate calculation, polynomial speed up for the reaction diffusion dynamics. So in that case, we basically can establish some kind of like a framework for the potential quantum advantage in the fault-tolerant computing era. So this work is supported by the laboratory research and development initiatives, and we are aiming to basically provide a circuit-based end-to-end resource estimation in solving these multi-scale nonlinear complex systems. And eventually, we hope to have the first real implementation in the FTQC area on 100 qubits. So this required a lot of detailed optimization and develop new quantum algorithms that can really tackle the strongly nonlinear system. Thank you.
Wonderful. Thank you, Xiang-Yu. Questions from the audience?
Thank you for your poster. I'm curious. So it's, from what I can tell, ultimately you're using a quantum linear systems algorithm. Is that correct? Like that happens after you do the nonlinear to linear transformation?
Right, yes. Basically, it's a quantum linear system solver. The key idea here is really to reformulate the fluid dynamics to mitigate the nonlinearity. Yes.
And so I assume, like most, you have maybe condition number issues. Have you looked at preconditioning at all? Is that coming into effect in any way?
Oh yeah, here somewhat we bypassed this like condition number restriction by this linear combination Hamiltonian summation, because there the quantum complexity scales only with the norm of your coefficient matrix. So we can prove in this case that the norm of the coefficient matrix does not scale with the number of grid points that you have.
Okay, that's really interesting. I'll have to read more about it. Thank you.
Thanks again, Xiang-Yu. And then we go to our fourth speaker, Julien Zylberman from the European Center for Research and Advanced Training in Scientific Computing. Julien, please go ahead.
So I'm a senior researcher at the Fairfax Research Center in France, south of France, working on the development of quantum algorithm for differential equation, fluid dynamics, and in particular meteo forecasting. As we mentioned already in the conference, solving a nonlinear differential equation can be very challenging on quantum computers since quantum gates are linear and unitary, whereas partial differential equations that we are interested in are nonlinear. So the goal is to go from the red box on the top left corner to the green box on the bottom of this scheme. And to do so, the first step is to linearize the differential equation using either Kalman linearization, nonlinear mappings such as the Madlung transform, or embeddings into larger space such as the Liouville or Koopman-von Neumann mappings. Then from a linear partial differential equation, one has two strategies. The first one is to discretize space and time in order to get to a linear system of equation that requires to be inverted. The second possibility is to just discretize the space to get an ordinary differential equation and then use a quantum solver for ordinary differential equation. But even if one arrives to the green box, one has two remaining challenges. First, to decompose the unitary U, which is an n-qubit unitary, a very large matrix, into primitive quantum gates. And general methods to do so are not efficient, so one needs efficient quantum circuits to do so. And the second task is to prove that every arrow are efficient representation, are efficient approximation that enables to recover the physical solution at the end of the quantum numerical scheme. So please, could you go to the next slide? So in this work, we've simple convection equation with position and time dependent velocity field. And please, could you go to the next slide again? And the second problem that we consider is the anisotropic diffusion equation with an anisotropic diffusivity depending on space and time. And for these two equations, we have introduced a quantum numerical scheme composed of three steps: initialization to load efficiently the initial condition of the problem into a qubit state, evolution based on trotterization, and a measurement step to recover relevant quantity of the problems to do this efficiently with a tailored measurement protocol. Please, could you go to the next slide? Thanks. We've performed the quantum and numerical analysis for each step, proving that there are 7 sources of errors. And first, that the space discretization error decreases exponentially with the number of qubits per axis. And in the next slide, you'll see that the vector norm error of the trotterization approximation is also independent of the number of qubits thanks to a new bound, the vector norm of the commutator, that do not scale with the number of qubits compared to previous norm in the literature. So we've performed classical simulation of the quantum numerical scheme on very simple transport equations up to 18 qubits. And please, in the next slide, we've also performed some simulation of the diffusion equation up to 12 qubits with time and space dependent thermal diffusivity. And in the next slide, I have a lot of slides, I'm sorry. We've performed some simulation of the 1D transport equation on 3 qubits up to 250 gates on IBM quantum devices. And finally, in the last slide, if you are interested by this work, and if you want to learn more, you can look at my poster or these papers. Thank you very much for your attention.
Wonderful presentation. Thank you so much, Julien. Are there any questions from the audience? Yeah, there is a question from Xiang-Yu.
I just wonder, because the trotter method is like introduces pretty big errors, right? And also for time-dependent cases, a bit tricky. I wonder if you have considered other methods like the QSVT type.
So indeed, the trotterization is first very interesting in these examples because the trotterized operators are very easy to implement quantumly in terms of quantum gates. But the scaling, the asymptotic scaling of trotterization may not be the best compared to QSVT methods that allows to prove a logarithmic dependence of the error. However, implementing Taylor series or Dyson series associated with an exponential of a matrix can be very challenging. It was already the case classically, like 30 years ago. There is a paper like 19 dubious way of implementing an exponential of matrix on classical computers, and due to arithmetical error. So trotterization enabled to bypass some issue that you could have with Taylor or Dyson series of the exponential, even though the scaling is not the optimal one.
Excellent. Thanks again, Julien. All right. And then there is a question for you from the audience, Hedwig.
Thank you very much for a nice talk. I have two questions. The first one is to confirm that your quantum machine learning has not been run on quantum hardware. And the second thing is you said that you run a short time of a high resolution simulation to get data for training. And the high resolution, how high is it? Thank you.
Okay, so about the hardware. So we've only started recently working on quantum hardware, and so far the only one that we have been able to test was the cloud cover model, but this is only like really in the early stages and no training there, of course, yet. So only to see if the inference works. And then for the high resolution data, actually, I'm not sure since I'm not involved in that work exactly. I mean, the target resolution that we have is at 80 kilometers. So this is what we coarse grain to. Yeah, but sorry, I don't find the final resolution right now. So maybe you have to check the papers for this.
Yeah, and Hedwig's email address is here, so we will reach out to you for further information. Thank you so much. A warm applause for all 4 speakers.